He drifts in from the cold edge of the night sky and stops before an ancient lantern. It hangs against the starfield, bright enough to cast a pallor on passing comets, round enough to make geometry feel small, banded like a planet wrapped in ritual. Jupiter waits in silence while sunlight rakes across his face. From far away the scene is simple. Amber belts, pale zones, a red oval that seems to breathe. Closer, the simplicity dissolves. The stripes are not paint, the colours are not skin. The surface is not a surface. The planet wears a veil of clouds, and the veil has its own weather, its own chords and counterpoints, its own labyrinth of eddies inside eddies. Beneath that veil, sound would fall in on itself, light would bend through haze, and matter would relearn its name. The top of the clouds is a high plateau of thin air, colder than Antarctic winter, spread over a ball of gas 11 Earths wide. Hydrogen and helium dominate like an ancient hymn, repeated across most of the observable universe. Yet the accents on Jupiter's face come from trace ingredients. Ammonia condenses and whitens. Sulfur mixes and darkens. Water gathers in hidden towers, far below the bright frosting seen by telescopes. In this upper world, the pressure hovers near what a human lung would call normal, a familiar number attached to a thoroughly unfamiliar stage. Here, the winds race east and west along narrow highways. The planet spins in less than 10 hours, and rotation sharpens the winds into bands that circle the globe. Nothing stands still long enough to be named. A cloud born near dawn may be torn into feathers by noon. He listens, and the planet speaks in colours. Where the air rises, ammonia ices form pale zones. Where the air sinks, cloud tops clear, and the belts darken, revealing the warm glow of deeper layers. The palette is chemistry raised to the level of weather. Chromophores, complex molecules cooked by sunlight and electrical storms, give the browns their syrupy depth. Finer particulates scatter blue light and wash the whites with frost. The result is a face that looks painted, but is alive. A mask that looks still, but is in motion. There is gravity in those clouds that has nothing to do with mass, the gravity of mystery, because the eye sees only the first pages of a book written in pressure. Under the gauze of ammonia lie zones of ammonium hydrosulfide, where sulfur and ammonia bind in crystals that would never fall on Earth. Deeper still, the temperature climbs, and water becomes liquid in thunderheads that dwarf continents. Lightning forks through columns that climb dozens of kilometers from their bases, powered by convection that finds fuel in the planet's own heat. For Jupiter glows from within, leaking more energy than it receives from the sun, a slow exhalation left over from formation and stirred by exotic rain. The clouds are not a coat. The clouds are a billboard for a furnace that hides in depth. The veil misleads as much as it reveals. The human mind is trained by stone and ocean, by mountains with roots and seas with floors. Here, there is no familiar ground to stand on. The bright tops of clouds tempt the imagination to step, but a step would find vapour and fall. The line between atmosphere and interior blurs, because the atmosphere is the interior, only thinner and colder at the top. With each kilometre downward, molecules crowd closer, collisions come faster, and the softness of gas begins to imitate the firmness of a world. A hand that could reach through those layers would feel the change as a tightening in the knuckles, a pressure that climbs from gentle to bruising, then to a grip that does not let go. He watches the bands like arteries around a beating heart. They never break, yet they shear and meander. Embedded within them, ovals yawn and contract, filaments twist, and small storms pop like white candles against rust. Yet the choreography remains, sustained for years, for decades, sometimes for centuries. The planet's rapid spin carves the flow into jets that alternate direction with latitude. Each jet is a wall of momentum. Each wall guides moisture and heat, like a shepherd guiding flocks across a vast and trackless plateau. In the high atmosphere, sunlight paints shadows on this moving architecture. Ultraviolet burns, methane absorbs, and the planet's glow plays through the haze like late afternoon in a cathedral. The camera of the mind descends toward cloud level, and the scale shifts. What was a gentle stripe from afar is now a weather system bigger than Earth, threaded with turbulence, crowned with billows that explode in slow motion. The air is thin by human standards, yet it carries more power than any storm on Earth, because it has room to spread and time to grow. The planet's heat rises, the planet's spin redirects. The planet's chemistry sets the menu for what can freeze and what can rain. Out of this triad comes a melody that repeats but never repeats exactly, a jazz of pressure and light. The veil does not part easily. Even the best images miss what lies beneath. The eye is biased to photons. The hidden interior announces itself through different messengers. Radio waves hum from lightning and from electrons trapped in a magnetic field so large it would swallow a small constellation. Infrared reveals hot upwellings and cool downwellings. Ultraviolet paints auroral rings that brighten and dim as currents pulse through the unseen depths. Gravity tugs at passing spacecraft with slight but telling variations, the pull of mass arranged in patterns the clouds only half betray. The veil of stripes contains riddles written in spectrum and spin, in whisper and echo. He considers the origin of the colours again, and finds courage in the details. Ammonia condenses first because it can. It is abundant, it freezes at a temperature the high air can reach, and it floats like breath made visible. Water waits deeper because it requires more warmth to become vapour and more pressure to condense again. Once it does, it rules. Water carries heat and fosters lightning, it climbs through cells that vent energy, and it falls back as rain no human hand has felt. The depth of the water cloud deck decides how much darkness the belts will show. The strength of the sunlight decides how far chemistry will knead the colours into their final shades. A veil, yes, but a veil with meaning. He steps back, and Jupiter becomes an idea. A giant planet is a laboratory where gravity, rotation, and radiation meet in a regime that Earth cannot offer. Hydrogen and helium write most of the rules, but trace species author the plot twists. The stripes are a consequence of rotation that cracks the global circulation into lanes. The red and brown tones are a consequence of photochemical baking and sulfur stories. The bright whites are ice at the top of rising towers. The dark ravines are places where air sinks and warms, melting clouds back into invisible vapour. Each of these truths is a line in a larger poem whose bottom half is still blank. He looks again, and the veil thickens, not because knowledge has failed, but because wonder has succeeded. It takes courage to admit that a planet this close and this bright still keeps secrets in abstraction. Pressure is not directly seen. Conductivity is not directly felt. The point where gas gives way to something almost like a liquid is not a surface anyone can touch. Yet the visible bands keep pointing downward, like arrows. They urge attention into depth, ask patience from the imagination, and demand instruments that listen rather than look. The veil of stripes is not a wall. It is a window that has chosen to be frosted, inviting the visitor to trace figures in the glass and to infer the lights within. For now, the view remains a study in texture. He sees a world that has never known a coastline. He hears thunder that rolls without echo. He senses a clock that runs on heat, rising through chemistry, spun into threads by rotation. Stars pass behind, and the planet keeps weaving. A voyager might grow old watching those stripes and still be surprised by the next turn of colour, the next plume, the next sudden clearing that lets a shadowed depth glow. The veil is not there to hide. It is there to teach that not everything bright is simple, and not every mystery begins in darkness. Sometimes it begins in a band of pale cloud, sliding around a giant, humming with the quiet of an unseen world. He begins with a wooden tube, 2 lenses, and a winter sky. In January 1610, an Italian professor points the small instrument toward a bright star that refuses to twinkle. The disk he sees is not perfectly round, and beside it tiny sparks shift their positions from night to night. He sketches the pattern, waits, and sketches again. The sparks exchange places in a rhythm that hints at obedience to a hidden order. He names them after patrons, yet the act is not flattery, it is revolution. 4 small worlds circle a larger one, and the Earth no longer holds the exclusive script for motion. With that patient week of drawings, astronomy acquires a method, comparative and relentless, a way of learning by watching change. Across Europe, the news travels faster than the seasons. Others build better tubes, refine the mountings, polish the glass. Eyes convert to instruments, and the planet becomes an object that can be measured rather than admired. The disk shows bands that shift in shade, and the very rotation of the world can be timed by following features that drift around the circumference. It is not a perfect sphere. It bulges at the equator. A truth inferred from how quickly the features return to view. Rotation links to flattening links to internal heft, and already the path from appearance to essence is open. In Paris and London, observers trace a stain that refuses to vanish. One year it darkens, another year it pales. The stain is oval, and its patience is unnerving. It invites speculation about a storm larger than continents, a vortex that may outlive generations. The notion that weather could persist like architecture changes what a planet can be in the human mind. There are no continents on which to anchor direction, yet there is a memory in the atmosphere itself, a memory that endures enough to be followed by astronomers who inherit each other's notebooks. Spectra arrive, brought by prisms and slits that separate light into fingerprints. At first, the planet's reflected glow looks like a soft echo of solar light. Then narrow gaps appear, places where particular colours fade. Each gap is a missing voice in a choir, and each missing voice belongs to a molecule. Methane leaves its pattern, ammonia leaves another, and the outer planet begins to sound like a cold laboratory in the sky. The list of ingredients grows, and with it, the confidence that chemistry can be read at a distance. The planet is no longer just a shape and a dance of moons. It is a mix, a temperature, a pressure that can be estimated with math and glass. Radio instruments join the chorus. In the middle of the 20th century, a pair of antennas detect a hiss from the direction of the planet, a restless noise that rises and falls. The hiss does not match the sun, and it does not repeat like a star. It behaves like trapped electrons, spiraling along magnetic fields, and it hints that the world is not only massive, but also threaded by currents. Over time, patterns emerge in the radio arcs, linked to rotation and to places near the poles. The notion of a magnetic leviathan begins to form, and the planet's unseen interior acquires a new outline, traced by electrons rather than by light. The space age changes pace into stride. A small spacecraft crosses the asteroid belt with a heat shield and modest cameras, braving a radiation environment that few had ever quantified. Pioneer 10 skims the giant's flank in 1973 and returns images that show bands with startling clarity. It also returns data on charged particles that bite into electronics and threaten survival. Gravity bends its path, and the spacecraft escapes the planetary realm entirely, but not before making the planet a navigational partner. A year later, a twin repeats the dance and adds measurements of the magnetosphere's size and temper. The giant acquires a voice in particle counts, in field strengths, in shock fronts where solar wind meets planetary breath. The next visitors carry better eyes and more intuition about what to ask. 2 voyagers arrive in 1979 and start drawing a map of phenomena that no one had predicted in detail. Their cameras find thunderheads that punch into sunlight, lightning that flares in the night side, and a ring so faint it seems to hesitate between existence and rumour. A moon erupts with fire, painting plasma into space and feeding currents that close through the planet's poles. Auroras bloom like living curtains, and the atmosphere answers with emissions that explain some of the earlier radio whispers. With each frame, the question shifts from what is there to how it all fits, a change that always marks the transition from discovery to understanding. A new idea takes form. Photographs are a beginning, not a verdict. To know the depths, something must go in. Engineers design a machine that can separate from its mothership, fall alone, and listen with instruments built to fail only after their purpose is met. The journey is long, the route indirect, and the arrival violent. In December 1995, a blunt cone enters at hypersonic speed and survives long enough to taste a segment of sky. Sensors drink the air and transmit while batteries last. Winds blow harder than predicted, dryness extends deeper than comfort allows, and lightning announces itself with electrical pops. The numbers upset simple pictures, but they give the planet weight in measurement rather than myth. After the cone is lost to pressure and heat, the orbiter continues, mapping clouds in infrared, tracking storms, watching moons pass, and relaying a message that the world is more complicated than any single descent could prove. Other missions fly past and add pieces to the mosaic. One probe aimed for Saturn borrows speed from the giant and so takes a portfolio of images and fields. Another, headed for Pluto, uses the encounter to test navigation and to glimpse the planet's poles with modern eyes. Each brief visit is a stroke on a larger canvas, and each stroke confirms that small changes at the top layer may hint at deeper patterns below. Lightning rates vary with latitude, ammonia hides and returns, and temperatures draw gradients that circulate like whispered instructions for the winds. An audacious plan takes shape to reject equatorial approaches and to circle from pole to pole. The choice is both aesthetic and practical. The most dangerous radiation belts are avoided by swinging over the north and south like a pendulum, and the view becomes emphatically new. Cameras look down on polar caps that are not caps at all, but fields of cyclones arranged in geometric clusters. Microwave eyes peer through cloud decks and read the brightness of layers that visible light cannot access. Gravity measurements borrow the subtle tug on a spacecraft's path and translate it into harmonics that betray where mass concentrates and where it diffuses. Magnetic maps acquire fine detail, revealing folds and offsets that place the dynamo in a restless, asymmetric heart. With each pass, models are challenged and rebuilt. The old thought of shallow weather gives way to a picture of winds that sink thousands of kilometers. The imagined sharp boundary within becomes a gradient that smears rock and ice into a fuzzy region where elements mix and settle. Helium seems to separate from hydrogen at depth, a rain that releases heat and alters how energy escapes. The magnetic field refuses symmetry, and the auroral footprints of moons etch bright loops into polar glow. The list of instruments matures into a list of questions asked in precise dialects. How deep are the jets? How heavy is the heart? How is heat carried? Where do currents turn and climb into space? The story of discovery is not only about tools, it is also about patience. Observatories on Earth keep watch through seasons and solar cycles, catching changes that cannot be captured in a single flyby. New instruments on large telescopes pick out spectral lines with cruel sharpness, measuring ammonia and water in ways that once required a parachute. Radio arrays trace emissions from electrons that reveal the magnetosphere's pulse against the sun's changing wind. Infrared eyes detect flashes that betray bolides slamming into the atmosphere, reminders that the planet is not a closed system, but a participant in a wider debris field. Each decade adds a layer of understanding, and each layer modifies the silhouette of the unseen. From a wooden tube to a polar orbiter, the arc bends toward depth by inference. Moons teach lessons about formation and tides. Radio hiss teaches lessons about fields and charged particles. Spectra teach lessons about chemistry and temperature. The planet resists any single portrait, yet the portraits integrate, as if the object prefers to be approached from many angles and only then to be sketched with confidence. He continues to look, because looking has never been passive in this pursuit. Daylight telescopes follow cloud features and compute rotation drifts. Nighttime receivers collect the storm static that leaps across megahertz and tells of convective towers in the dark. Spacecraft alter course by a handful of meters per second to skim closer to the gravity well, and from that, slight adjustment flows a harvest of interior clues. Each measurement, whether it tastes air or listens to a wave, is a modest act of trust that the planet will answer. It does answer, And the answers are subtle, rarely strident, often encoded in a language that took centuries to learn. Discovery so far has been a choreography of lenses, antennas, accelerometers, spectrometers, and heat shields, each teaching the next what question to ask. The small sparks seen in 1610 are now worlds with volcanoes and oceans and iron cores. The bands that once seemed like decorative stripes are tracked as moving constraints on deeper flows. The magnetic growl that once puzzled a radio dish is now a living map of currents drawn across auroral ovals. The planet has become intimate without becoming simple, familiar without losing scale. The path forward sits in the same instruments refined, in new ones imagined, and in the same resolve to listen longer and with fewer assumptions. The journey from first glance to polar plunge has not merely filled a ledger, it has altered the grammar of inquiry. A giant planet is a teacher, and the course is taught in reflected sunlight, in thermal glow, in the tug of gravity on a passing machine, and in the hush that follows a probe's last transmission. In that curriculum, discovery is not a moment, it is a lineage, and Jupiter has adopted generations of instruments and minds into it. He falls out of sunlight into a roar that melts stone. A bullet of alloy and sensors reaches a world-sized wall of air at a speed that leaves words behind. Shock wraps the capsule in a sheath of plasma. The skin ablates into a charcoal cloud that peels away in curls and sparks, and the world below accepts the visitor as friction and fire. Instruments sleep through the furnace, counting nothing, because the only number that matters in those first moments is survival. When the pressure rises and the heat slackens, charges arm, relays click, and the capsule becomes a laboratory. A parachute blooms in chemically heated sky, the heat shield drops into darkness, and the conversation begins. The pressure at this height would not bother a strong lung, yet the air is hydrogen and helium. The parachute rocks as if it understands the scale of the vault below. A structure package measures acceleration and finds the telltale wiggles of turbulence. Temperature climbs by clean increments, a gradient insistent and precise. The parachute line trembles with gusts, and the Doppler tone sent back to the mothership shifts by fractions of a note that encode wind. The wind is faster than any common storm on Earth. It surges past 150 meters per second, then presses toward 170, and it does not fade with depth. The atmosphere behaves like a vast river in a canyon. The deeper the river flows, the more it steadies, and the probe sways in that current as if tethered to an unseen hand. A nephelometer throws light into the surrounding haze and counts backscattered photons, an optical way of asking whether clouds are present. The answer is a surprise. Trace mists appear, then gaps open, then a thin layer glints and passes. The expected bright deck of ammonia ice is there, but not generous. Below, the instrument looks for an ammonium hydrosulfide layer that theory had promised. Evidence is faint and uncertain. Water cloud formation remains elusive, as if withheld. The radiometer feels upward and downward energy, and senses a sky that is stingy with condensate. The descent path has slipped into a hot spot, a window of unusually dry air where infrared brightness had long hinted at warmth below cleared cloud tops. The choice of entry point becomes destiny for interpretation. The probe is tasting a drought in a land famous for rain. A neutral mass spectrometer opens its mouth against the wind and drinks molecules. Hydrogen dominates, helium follows, methane whispers of carbon abundance, ammonia breathes a variable signature. The instrument counts noble gases with the patience of a jeweler. Argon numbers rise to levels richer than the solar mix by a factor of 2 or 3. Krypton and xenon also stand elevated. Neon is strangely scarce. Helium itself sits low compared with the primordial recipe. The ratios sketch an origin story in the shape of data. Heavy, noble gases could have been delivered on ices that formed in deep cold, or captured in a way that favoured those elements. Helium and neon, depleted together, hint at processes at depth that sort and sequester, a quiet rain of helium into layers where neon follows, dissolving into droplets that fall. The lightning and radio emission detector waits for crackle. It hears a world largely silent along that path, as if the dry column resists spark. The orbiter elsewhere confirms that lightning does haunt the planet, but the instrument carried by the parachute records only restraint. Chemistry controls charge separation, water controls updraft vigor, and the drought aloft starves the storm engine in this corridor. The quiet does not mean absence on the globe. It means a portrait taken in a quiet street. The helium abundance detector refines the gas mix with a focused method that exploits sonic resonance. Its verdict, when combined with the spectrometer, strengthens the hint from neon. Helium is low by a few points compared to the solar original. The implication is a separation at depth, where hydrogen and helium cease to behave like a simple mixture, an unmixing that encourages droplets of helium to condense and fall. Each droplet carries energy as it sinks, releasing heat into surrounding layers. The probe does not go deep enough to watch this rain fall, yet the signature appears in the simplest of measures, the ratio of two most common elements in the universe. The Doppler wind experiment turns the planet into a wind tunnel. The signal transmitted by the probe is tracked by the orbiter and relayed to Earth. Small shifts in frequency decode into a vertical profile of motion. The profile astonishes. Rather than dropping off below the clouds, the wind strengthens and persists. The notion of a shallow weather layer governed only by sunlight fades. Momentum runs deep, carried by columns that feel planetary rotation and pressure gradients far below the bright facade. At 4 bars, then 10, then past 15, the wind refuses to yield. By 22 bars, the instrument still reads strong flow. A message is delivered in clean physics. The engine of the belts does not live only at the top. The structure instrument keeps its watch. Pressure climbs past values seen at the bottom of Earth's oceans. Temperature crosses the threshold where water would boil at sea level and keeps going. The parachute holds until its schedule speaks. Then, at a planned mark, it is cut away so that the probe can drop faster and reach deeper before batteries fail. Telemetry continues as the air thickens. The walls of the capsule creak. The craft is small, and the forces it endures are large, but measurements retain their calm cadence. Acceleration hovers around a steady fall. The brightness sensors record less scattered light as the haze grows. Still, the clock ticks and packets fly. Another instrument counts aerosols and finds that even in a drought, microphysics persists. Small particles wax and wane with altitude. A tantalizing transition suggests that condensation and evaporation are dueling in layers only kilometers apart. The radiometer reads net flux and suggests that energy is being transported upward from warm depths into cooler heights. The planet glows from within, and the probe measures the gradient through which that glow climbs. A record of heat flow is written into the data stream one sample at a time. Numbers on water vex the team even as they are welcomed. The mass spectrometer reads less water vapor than anticipated, even when the probe passes the zone where a water cloud should reside. Deeper still, the promised rise to a well-mixed abundance fails to appear. The parachuting laboratory is threading a ribbon where downwelling air is dry and warming, a corridor that suppresses condensation and masks the broader inventory. The lesson is subtle and stern. A single path into a giant world samples a weather pattern, not a planetary mean. Even so, the drought itself becomes a discovery. Hotspots are not illusions in infrared. They are functional windows into deeper, warmer layers and are tied to the very engine of the belts. The final minutes are a steady narrowing of horizons. Pressure approaches 22 bars, temperature climbs past 150 degrees Celsius, and the electronics shorten their sentences. The wind measurement holds strong. The gas mix continues to assert helium's modesty and the nobility of argon, krypton, and xenon. The instrument tally stands complete enough to change textbooks. Gravity has bent the trajectory into a tight arc relative to the vast curvature of the planet. Yet for the probe, it is a simple fall. The voice fails with no drama, cut by heat and pressure that care nothing for achievement. Silence returns to the radio spectrum. What remains is a footprint in data that shifts the center of interpretation. Winds reaching deeper than comfort suggests, water hidden by meteorology, noble gases enriched beyond simple capture, helium rain implied by ratios, lightning quiet in one column despite global energy, and a thermal profile that speaks of interior heat flowing outward. The capsule carried a small suite of instruments, but the story it wrote is multitudes. Weather on this world is not a skin but a volume. Chemistry is not uniform with height. Dynamics stitch the layers with threads under tension, and those threads tug at models until they reshape. The cloud tops regain their distance. Far above the path of descent, belts continue to stream, spots continue to roll, and auroras flare when currents close through polar sky. The single fall through a dry corridor becomes a confession that a planet this large must be met with patience and a willingness to be surprised. The first taste is instructive, brave, and incomplete by design. It sets the stage for instruments that would read gravity like sheet music and magnetic fields like braided ropes. It also grants the humbling clarity that to know the depths, one must accept that the sky of a giant is a landscape of its own, divided by rivers of wind and sculpted by heat that was born when the world itself was young. He listens where the eye is useless. The planet becomes a set of forces that touch an instrument without showing a face. Light can be deceived by cloud and colour. Gravity cannot pretend. Magnetism does not care about hue. Radio waves thread the atmosphere and return with a memory of what they have crossed. The surprise is not that these messengers exist. The surprise is how strongly they speak, and how much of the planet they describe without a single image. A passing spacecraft flies a path so precise that a shift of a few millimeters per second matters. The pull on that path is not uniform. It wobbles in tiny patterns that repeat from pass to pass, and those patterns can be decomposed into harmonics. The coefficients carry names like J2 and J4, abstractions that capture where mass is slightly more or slightly less concentrated. The numbers insist that the world is not a simple, rigid rotator. They imply that vast belts of wind add their own weight to the gravitational field, deep enough to matter, broad enough to shape harmonics that alternate between even and odd. The eye sees stripes and guesses at weather. The invisible says the jets reach into the interior like roots. Another instrument reads a field that is everywhere and nowhere at once. A magnetometer turns the void into a script of direction and strength, point by point along the track. The field refuses to behave like a neat bar magnet. It twists with asymmetries, clusters of strength, and quiet pockets that do not match simple formulas. The dipole tilts and wanders. Higher-order components stand out like knots in a rope. The map hints that the planetary dynamo does not occupy a perfect shell. Instead, it breathes in a volume where conductivity rises with depth, where flows of metallic hydrogen shear and curl, and where composition may vary across gradients that steer electric currents. The field is intimate, restless, and strangely lopsided, as if the heart of magnetism had shifted its chair. Radio receivers turn the planet into a storm of whispers. At decametric wavelengths, bursts erupt in patterns tied to rotation and to the position of a volcanic moon that drags a torus of plasma around the equator. Electrons stream along magnetic lines, and when they enter regions of stronger field, they gyrate faster and sing. The song carries the signature of the cyclotron frequency. It reveals where the field tightens and where it relaxes, a map drawn by charged particles rather than by light. At shorter radio wavelengths, a smooth glow emerges from the belts of electrons trapped close to the planet. This synchrotron emission originates deep within the magnetosphere and outlines the regions where radiation is fiercest. Cameras would be blinded by brightness. Radio simply listens and sketches halos. Microwave eyes look through the top clouds and measure the brightness temperature of layers far below. Different wavelengths penetrate to different depths, so a spectrum becomes a vertical profile. Ammonia absorbs microwaves, and its abundance sculpts the pattern. Where the signal is dim, ammonia is rich. Where it brightens, the air is dry. The result is a map of a gas no human can smell there, spread over latitudes and longitudes, hidden beneath visible tops. The picture confounds simple symmetry. Patches of dryness alternate with columns of richness. Some align with belts and zones, others cut across them. The planet reveals that chemistry and dynamics are tangled in depth, and that the cloud deck is an unreliable narrator. Occultation events add another invisible layer of truth. When a star slips behind the limb of the planet, its light softens and vanishes through refraction. The rate at which the star fades encodes the temperature and density structure of the upper atmosphere. When a spacecraft's radio signal skims the limb, it bends through gradients of refractive index and arrives at Earth distorted just enough to be measured. Pressure and temperature emerge from the distortion. No eye could make out a curve that subtle. A clock and a receiver can. The profiles they retrieve describe thermal tides, polar warmings, and latitudinal variations in scale height that reveal how energy is moving aloft. Auroras circle the poles like gates to an inland sea of currents. Ultraviolet and infrared instruments weigh the brightness, line by line, to recover the precipitation rate of electrons and ions. Each brightening event is a handshake between magnetosphere and atmosphere. The entire system becomes a circuit. Solar wind compresses the outer field. Rotation flings plasma outward into a disk. Moons inject sulfur and oxygen. Field-aligned currents close through the ionosphere, and the glow answers in time. No photograph conveys the accounting of power. Spectra and timing do. They show that the planet generates much of its own auroral energy by the spin of its mass and the drag of plasma. A lantern powered by rotation, as much as by the sunday. The invisible also speaks in tremors too slow for hands to feel. Instruments search for global oscillations, subtle pulsations that travel around the planet like waves on a bell. The frequencies depend on compressibility, on stratification, on the stiffness of deep layers. Detecting them is difficult amid winds and noise, yet attempts have teased signals that suggest the giant does ring. If confirmed with greater clarity, those tones would be a seismology of gas, an unprecedented way to weigh the blurred boundaries where molecular hydrogen gives way to metallic behavior. The concept is daring, but the physics is patient. Every world has natural modes. Some simply require more silence to hear. Energy balance hides in wavelengths a camera cannot see. Infrared spectra reveal a planet that glows with internal heat. The flux exceeds the sunlight absorbed. The surplus must come from contraction, from settling of elements, from rain of helium in depths where solubility changes with pressure and temperature. Radiative transfer models reconcile the upward glow with the vertical profiles. Convection must carry energy through thick layers, yet it may not be free to mix everything uniformly. The invisible balance sheet forces a revision of how heat escapes from giants, and it suggests that layered structures throttle the flow like baffles in a chimney. Even gravity can be watched for changes with latitude and time. By comparing multiple passes, subtle shifts in harmonics hint at movement of mass that can only be carried by winds. The jets thus gain a second identity. They are not only surface features, they are generators of gravitational fingerprints that vary as flows adjust. The insight is sharp and almost disorienting. A pattern the eye calls weather acquires the dignity of a geophysical load. From the outer field to the inner currents, each invisible measure points inward. None of it depends on a clear day. None of it cares for colour. A magnetometer flying in darkness will still record the twist of lines. A radio receiver pointed at night will still catch a storm of electrons. A gravity experiment will still feel the tug beneath silent clouds. The astonishment lies in how much agency a planet expresses without ever showing itself. The tools that listen become more important than the tools that look. The invisible also argues for humility. A field map can be misread unless one knows how flows shape conductors. A gravity harmonic can mislead unless one accounts for winds that dredge and deposit momentum across depth. A radio burst can be attributed to the wrong engine unless one traces the geometry of moons and magnetic longitudes. Yet these warnings do not weaken the evidence. They strengthen it by pruning fantasies and narrowing the space where conjecture may wander. In that narrowed space, theory and measurement face each other with fewer masks. The most arresting realization is simple. The essential story is written in forces and waves, not in pigment. A planet made mostly of hydrogen and helium leaves few visual clues by design. It speaks through push and pull, through field and current, through glow and absorption in bands the eye never learnt in childhood. Instruments translate that language into plots and maps that, once learned, feel as intimate as any photograph of a storm. The shock is not the difficulty. The shock is the intimacy granted by what cannot be seen. He studies a globe run by invisible arithmetic. The bands that girdle the planet are not decoration. They are conveyors of heat, momenta wound tight by spin, and they braid the weather into an engine that refuses to behave like anything on smaller worlds. The rules begin with rotation. A day that lasts less than 10 hours sharpens every motion. The Coriolis influence becomes a sculptor of oceans of gas, turning straight paths into arcs and splitting the flow into alternating lanes that circle latitude after latitude. Each lane is a jet. Each jet is a wall. Between the walls, turbulence blooms, and then is sheared into filaments that march along the band until the next jet steals them. Energy enters from below and above. Sunlight warms the top, but the more stubborn power comes from within, a long memory of formation mixed with slow settling of elements. That internal glow rises through layers that conduct and convect, and along the way it is ambushed by chemistry. Water condenses where pressure and temperature permit, ammonia freezes higher, and both release latent heat that stokes updrafts. In a thin atmosphere, such processes make storms. In a giant, the same processes build conveyor belts that run for tens of thousands of kilometers. Upwelling enriches some latitudes with fresh condensates, downwelling dries others into brown clarity. The engine chooses its lanes, and the lanes wear their colors like uniforms. A theorist draws a line on a board and calls it the Rhine scale, the length at which turbulence stops cascading isotropically and begins to organize into jets under planetary rotation. On a globe this large, that critical scale is not a few hundred kilometers, but thousands. The consequence is counterintuitive. The bigger the world, the more the chaos self-arranges. Small swirls merge into larger ones, and larger ones feed momentum into the nearest jet until the jet stands up like a ridge in a desert of sand. Yet the ridges are not immovable. They meander. They exchange angular momentum with eddies that form and die. They pulse with waves that carry whispers of momentum across long distances. He looks at the equator and sees a special case. There, the dominant jet runs eastward with immodest speed. Kelvin waves and gravity waves surf along it, textured by convection that rises in patchwork. The result is an equatorial belt that can suddenly brighten with plumes and then relax into calm, a breathing that seems to follow a rhythm. High above, temperatures flit between warm and cool in a pattern that repeats over years, an oscillation that resembles a heartbeat in the stratosphere. The heartbeat modulates the reach of waves, and the waves adjust the distribution of momentum, as if a metronome clicks overhead while the orchestra of jets modulates tempo below. Storms fold into this symphony with their own thermodynamic agendas. In the belts where air sinks, clearings reveal warmth radiating from depth. In the zones where air rises, tall towers hoard ice and release electrical fury. When water condenses, it dumps heat in a rush, making buoyancy that can punch upward faster than local sound can reorganize. When hail forms in the cold cores of these towers, it carries heavy elements downward as it melts and falls, a freight of entropy that deepens the overturning. The consequence is not merely lightning and cloud, it is momentum transfer. Ascending columns and compensating subsidents torque the air around them. The torque feeds the nearby jet or steals from it, depending on latitude and phase of the surrounding wave field. He watches a belt fade and return. Once in a while, a prominent brown ribbon pales under a froth of high clouds, then disappears into a white shroud that looks almost serene. The serenity is camouflage. Below the new veil lies an uprising of convection that has stolen the belt's heat and hidden it in ice. Weeks or months later, dark gaps rifle through the whiteness as downdrafts drag dry, warm air up from below. The belt reappears like letters revealed by heat. This cycle announces that the engine runs on stored energy as well as on constant flux. It can load, lock, and release, a thermodynamic cycle writ in planet-scale calligraphy. The great ovals teach another lesson. Vortices embedded in the bands steal shear from the jets and return it as stability. Some swirl for years, tugging on the nearby flows, eating smaller tempests that wander too close. Their survival depends on a delicate balance between radiative cooling at the top, convective heat at the base, and the relentless shredding that the jets would inflict if left unchecked. These ovals flatten into ellipses, tilt with latitude, and sometimes change colour as chemistry inside them differs from the air they trap. They are not merely passengers, they are gears in the machine, adjusting the rate at which momentum is exchanged between neighbouring lanes. He turns to the mathematics of potential vorticity, that strange, conserved quantity that acts like a fingerprint for rotating fluids. Where it is uniform, flow can meander. Where it steps sharply, barriers form. The planet's alternating jets carve out a staircase of potential vorticity, each step a latitude where mixing is stifled. The steps defend the structure of the bands. They also imprison tracers, keeping ammonia-rich air where it rose and dry air where it sank. When a wave breaks across a step, the barrier yields and mixing surges, and the colour of a belt or zone changes in weeks. The physics is austere, the image is gorgeous. Microwave maps and thermal profiles add riddles to the engine. Some latitudes that look identical in visible light hide very different ammonia inventories beneath. Dry belts sit beside wet belts, yet the deep contrasts do not always line up with the cloud-top palette. This mismatch hints at a vertical tilt in the circulation, a slanting of upwelling and downwelling columns, so that the chemical walls no longer match the walls seen by the eye. The engine thus acts in layers that talk to each other imperfectly, passing hints upward in heat and downward in downdrafts, but rarely surrendering a full confession in any single band. He listens for waves with long wavelengths and patient teeth. Planetary Rossby waves roll around the globe, exchanging vorticity with jets and storms. Some anchor to certain longitudes, influenced by the combined drag of moons and magnetic stresses. Others run free, speeding or slowing as the background wind changes. Gravity waves launched by thunderstorms in the deep tropics ripple upward and outward, the way a bell's tone radiates through its body. When those waves deposit momentum, they shape the jets subtly, nudging a speed here, trimming a shear there, whispering into an engine that hears every nudge. Thermodynamics in this realm refuses the neat closure taught in smaller classrooms. Convection does not simply fill a layer then yield to radiation. Moist plumes entrain dry air and detrain moisture into sheared environments that carry it across longitudes before it can fall. Radiative timescales lengthen with depth, so heat released by condensation can pool into thermal anomalies that advection stretches into ribbons. The ribbons, in turn, feed or starve jets. The machine is a chain of feedbacks. None is perfect, all matter, and the final tempo emerges not from a single governor, but from the consensus of many competing processes. He imagines the bottom of visible weather, not as a firm lid, but as a reach where turbulence grows heavy. There, molecules are crowded enough that the flow forgets some of its two-dimensional habits and remembers that vertical motions carry weight. Jets that seemed immortal at the top blur into broad rivers that wander through layers of changing stability. If compositional gradients live there, they will damp mixing while allowing heat to pass in lurches. If rain of exotic droplets falls from above, it will seed additional layers of contrast. A storm world becomes a layered machine, and every layer delays or accelerates the traffic of energy. Nothing in this engine is left to accident. The rotation sets the lanes. The inner warmth supplies the budget. The condensable species pay out in bursts of latent heat. The waves carry news. The jets enforce order while they feed on chaos. When a belt fades, it is the result of a rearrangement of that budget and those barriers. When an oval persists, it is proof that the flow can decide to be a structure rather than a blur. the whole becomes more than pebbled clouds. It is a giant heat engine that parcels its own fuel and regulates its own exhaust without a coastline or a mountain to interrupt it. He leaves the globe in his mind with a new sense of scale and patience. The engine does not offer simple secrets. It offers patterns that hold for years and then astonish. With an exception, feedbacks that look linear until they lean into non-linearity, and cycles that hoard potential until a threshold invites release. The anatomy of this storm world is the anatomy of a living equation, one that never stops integrating, never stops exchanging energy between long waves and short eddies, never stops balancing warmth from within against sunlight from above. It is a machine built from gas and rotation, and it closes its own loop with grace. He lingers over a crimson oval that refuses to die. It occupies a corridor between jets that hurry in opposite directions, a whirlpool set inside a planetary racetrack. The eye sees a bruise the size of a world and imagines a surface gale. In truth, it is a tower of vorticity, a spinning mountain of air that arches above its surroundings and digs beneath them. The crest is cold because it climbs high. The base is warm because it reaches down where pressure turns heat into memory. Color is an accident of chemistry and light. Longevity is not. The vortex has learned how to drink from passing currents and to send its momentum downward along invisible columns that the planet's spin carves out of fluid. At the top, thin sunlight paints brick and rust into the haze. The pigments likely belong to molecules cooked by ultraviolet rays and lightning, then trapped in the slow gyre that circles the center. Around the rim, a collar of white curls where rising air condenses. Inside that ring, the atmosphere is drier and redder. The rotation is anticyclonic, turned westward relative to the planet's spin. The speed is not reckless. It is persistent, a procession of winds that complete an orbit in days, and then do so again. The balance is delicate. Pressure lowers toward the edge, centripetal forces keep the flow curved, and slight temperature lapses hold the roof high. This is not a storm in a frenzy. It is a monument to balance under rotation. Beneath the familiar face, momentum does not vanish. It threads downward along columns aligned with the axis of spin, the way a spoon's swirl in thick cream reaches from surface to depth. The planet's rapid rotation encourages such coherence. Stratification and composition set the limits. Where layers allow, the swirl becomes a Taylor column, a structure that carries the memory of rotation far below what any camera could see. Gravity readings and microwave glimpses imply that this particular monument plunges hundreds of kilometers. Not a few cloud decks, but a genuine reach into regions where ammonia is still a player, yet radiation is slower to act. The vortex is not a skin effect. It is an organ. As it digs, the whirlpool changes its trade with its surroundings. At the top, radiative cooling chills the crown and strengthens the pressure gradient that keeps the air turning. At depth, warmth from below intrudes along isentropes that lean with latitude. Those intrusions tilt the vortex, not randomly but in ways the jets and stratification permit. The whole column precesses ever so slowly, buffeted by passing eddies like a lighthouse pushed by tides. In that slow dance, the swirl leaks momentum downward. The leakage is not a loss. It is an investment in stability. The deeper the signature, the harder it is for shallow turbulence to erode the core. The corridor that hosts the vortex is a place of shears. To the north, a jet runs east. To the south, a jet runs west. The difference in speed across a few thousand kilometers is a knife that could slice lesser swirls to ribbons. This one survives because it sits at a sweet spot where the shear feeds it rather than undoes it. Small vortices, shed by baroclinic instabilities, wander into the neighborhood and become food. They merge with the perimeter, adding their spin. Filaments that try to peel away are wrapped back in by the guiding jets. The result is an economy. Energy that would have succumbed to a general cascade is recaptured by the great oval and converted into organized rotation. Waves ride the rim and radiate away. Those waves are the price of order. A stable vortex in shear must trade momentum with its environment constantly. It does so by spawning gravity waves that ripple upward and planetary waves that travel around the band. The ripples carry angular momentum to places where it can be absorbed without injuring the core. The planetary waves rearrange potential vorticity steps nearby, sharpening or blurring barriers to mixing. In this way, the red oval speaks to the broader engine. It is not a spectator. It is a negotiator that constantly pays its rent through wave radiation while drawing interest through mergers with smaller storms. Thermodynamics keeps the bargain honest. Moist convection lurks in the flanks, especially where the vortex scrapes against belts that breathe warmth from depth. Lightning sometimes fires in cells that form near the rim, where vertical motions sharpen and where hail and rain can shuttle heat and heavy elements. These bursts, though episodic, matter. They adjust the vertical density profile that keeps the vortex buoyant aloft and grounded below. The core prefers a certain stratification. Too stable, and it would decouple from the jets above, becoming a lonely island. Too unstable, and it would be flooded by convective chaos. It walks the line between the two, and in that poise lies its famous persistence. The colour is an index, but not a cause. Chromophores accumulate where air lingers, and the vortex makes air linger. Photolysis creates complex molecules that absorb blue and green light. Over time, the trapped haze deepens the hue. When chemistry shifts or vertical motions change, the shade can retreat toward orange or advance toward brick. The shrinkage seen in the oval's outline over recent decades adds another layer of intrigue. A smaller vortex can spin faster to conserve angular momentum, but it also becomes more sensitive to shear. The column beneath adjusts, perhaps narrowing while maintaining depth, perhaps losing some reach as the feeding rate changes. No single rule decides the outcome, but the presence of a deep root grants resilience against superficial insults. He imagines a cross-section through the vortex. At the roof thin, cold air holds elevated clouds. Near the centre, vertical motion gently rises, cooling and lofting hazes. Around the edge, air sinks to complete the circulation, warming adiabatically and clearing gaps where the red tints can shine from depth. Below the visible crown, the flow turns barotropic relative to the background, meaning the winds align more strongly with constant density surfaces. That alignment stabilizes the column against tilting. At yet greater depth, the differences in composition begin to matter. If helium separation has seeded layers with different mixtures, or if water gradients have built subtle steps, those steps can act as reflectors for the downward march of momentum. The column does not crash into a floor. It fades into regions where viscosity and stratification together persuade it to slow. Magnetic fields hover far below, born in metallic hydrogen, where currents flow like weather inside wire. The vortex does not reach that far, but its shadow might still touch conductivity gradients at intermediate depths. Any interaction would be weak and hard to isolate. Perhaps a whisper of drag, perhaps a shift in how waves propagate through layers with different electrical character. If such effects exist, they are small corrections on a story written in rotation and buoyancy. Yet, in a system, this large, small corrections can integrate over time into meaningful nudges, and the red oval has known time like few storms ever will. The interaction with neighbours is never trivial. Smaller anticyclones orbit like bees around a hive, sometimes merging, sometimes slingshotting away. Cyclones approach with gritted teeth, seeking to shred through filamentation. Each encounter rearranges the perimeter and sheds spirals that the jets carry off. In the wake of large interactions, the oval's altitude and temperature pattern adjust. The core may rise slightly, its crown cooling and brightening. The outskirts may thin, revealing darker reds as subsidence warms and dries the air. Even in quiet intervals, the rim is restless with filaments that peel and rewrap, signs of a boundary layer doing the endless work of matching a coherent interior to a noisy exterior. He listens for deep hints in shallow data. Gravity measurements taken during close passes report minute anomalies when the spacecraft flies near the vortex. Those anomalies can be inverted into estimates of depth and mass distribution for the column. Microwave brightness maps show how ammonia varies across and beneath the oval. Together they point to a creature that is hundreds of kilometers in depth, with composition gradients that differ from surroundings and with a thermal structure that supports a high roof and a stubborn base. The portrait is never final, yet it refuses any claim that the oval is superficial. Its signature endures below sight, below light, below the easy nouns of cloud and storm. The shadow in this context is not darkness, it is influence. The vortex's spin imprints patterns on layers it never shows. It modifies the stress field felt by the flanking jets. It seeds waves that tour the latitude band like messengers. It alters the path of tracers, concentrating chromophores and perhaps shepherding aerosols that affect how radiation is absorbed. It is a governor on variability, making the surrounding flow less free to wander than elsewhere. Remove it in thought, and the band would likely rearrange its balances in ways that would echo for months and years. He leaves the crimson oval with respect more than simple awe. A long-lived anticyclone on a fast-spinning giant is a thesis on stability under stress. It harvests energy from shear without being shredded by it. It breathes with radiative cooling at the top and with slow warmth from below. It throws part of itself outward as waves so that it can keep the rest. It carries a signature into depth that helps it ignore the insults of the moment, the red that invites the eye as a varnish. The true colour is the quiet certainty with which momentum finds a way to tunnel downward, becoming a scaffold that holds against the unending wind. He imagines a darkness where pressure turns intimacy into law. Hydrogen and helium fill nearly all the space, yet friendship between them is conditional. At gentle pressures they mingle without complaint. Far below, in heat that glows without light, and in pressures that crush the imagination flat, the partnership phrase. What was once a uniform blend becomes a strained marriage. Microscopic arguments begin along invisible boundaries in phase space. A droplet forms, not of water, not of metal, but of helium-enriched fluid that shrugs off hydrogen the way oil ignores water. The droplet grows, gathers neighbours, and starts to fall. The fall is slow by human reckoning, and swift by planetary standards. Each drop is heavier than the fluid around it, and gravity has eternity on its side. As the droplets descend, they meet regions where temperature rises and hydrogen grows more conductive, creeping toward metallic behavior. Some droplets dissolve again when conditions allow, surrendering their cargo back to the mix. Others survive to greater depths, coalescing into streams that turn into rain. The rain is not a brief episode. It is a climate inside a climate, a weather of atoms that plays over millions of years. With each meter of descent, gravitational energy converts into heat. That heat does not vanish. It warms the surrounding layers, thickens the blanketing against space, and alters the path by which interior energy escapes. The story begins with a curve on a phase diagram that no one can see directly. At certain pressures and temperatures, helium becomes less soluble in hydrogen. The curve defines an immiscibility region, a swath where the binary mixture prefers separation into pockets, rich in one component or the other. In the giant's deep interior, that swath is not a thin line. It is a band that cuts across layers already busy with convection, and with the slow creep of elements heavier than the main pair. Where the band lives, convection hesitates. Composition gradients stiffen the fluid. Pure heat can rise, but any uplift that tries to mix helium-rich fluid upward meets resistance. The result is a staircase of layers, each slightly different in composition and temperature, each passing heat to the next less efficiently than a fully mixed boiling pot would. At the top of this realm, a subtle signature travels upward. Helium is depleted from the gas that convects toward the visible atmosphere. The air near cloud tops ends up with slightly less helium than the primordial recipe predicts. Neon suffers even more, because neon prefers the company of helium. As helium separates into droplets, it escorts neon into the rain. The loss is a forensic clue, a whisper from the deep written into ratios at heights where a probe can breathe. Far below, the opposite occurs. Helium gathers, forms a reservoir, and may even build a shell of enriched fluid that rides atop regions where hydrogen behaves like a metal. The shell is more than a layer. It is a throttle on cooling and a lens for the planet's magnetic dramas. He considers the thermodynamics that hammers out this quiet rain. In the immiscible band, the free energy of mixing rises, so any fluctuation that enriches one pocket in helium becomes favored. That pocket grows, and surface tension encourages droplet formation. The droplets face a soup that is becoming more electrically conductive with depth, a medium where electrons move more freely as hydrogen molecules break and the fluid grows metallic in character. Falling through such a medium is an electrical as well as a mechanical act, but the drag is still dominated by viscosity and by the size of the droplets themselves. As they descend, they heat their wake. The heating increases local buoyancy in the hydrogen-rich surroundings, which in turn drives gentle upward flows. Each drop writes a thin column of exchange behind it, a molecular contrail in a sky no eye will ever see. This rain adjusts the clock of evolution. A planet that sheds helium from high levels and stockpiles it below cools more slowly than one that remains perfectly mixed. The extra heat from raining droplets prolongs the time the planet spends brighter than a naive model would expect. The topmost weather senses the effect as a persistent internal glow that keeps storms fed and belts warm from beneath. The interior senses it as a modulation of convection patterns and as a hardening of layers that resist full overturning. Over ages, the rain may migrate the boundary where helium is once again soluble. As the planet cools, the immiscible band shifts, and the rain's source region moves with it, like a monsoon line that drifts on a continental scale of time. He pictures a vertical cut from upper ammonia frosts to the metallic sea. In the high sky, chemistry and sunlight write colours on a moving canvas. A little deeper, water and electricity argue about thunder. Far below that, the mood changes. Hydrogen begins to forget it was a two-atom molecule. Electrons unpair into a shared pool. Conductivity rises by orders of magnitude. Somewhere above that transition lies the rain line, a sheet woven through the globe where helium begins to fall. In this sheet, convection is no longer simple. Warm parcels rising from below can shed helium as they cross the band, which changes their density independent of temperature. Cold parcels descending from above can gain helium and become even heavier, which accelerates their fall. These feedbacks steepen gradients and invite the formation of layers that act like thermal baffles. Magnetism keeps its counsel, yet the rain changes its context. The dynamo lives where hydrogen is metallic and flowing, likely in a thick shell wrapped around any central concentration of heavy elements. A helium-rich layer perched above that shell can affect how heat enters and leaves the dynamo region. Cooler tops and warmer bottoms adjust the vigor of the convective rolls that wind magnetic fields into strength. The field that emerges will reflect not only the speed of rotation and the conductivity of hydrogen, but also the fine print of heat delivery set by the rain. Irregularities in the field, odd offsets and patches of unusual intensity, could be read as the fingerprints of an uneven handoff from helium-stratified layers to the dynamo beneath. Instruments never see a droplet, yet the evidence multiplies. The gas near the clouds holds less helium than the Sunday neon is even rarer than expected. The planet glows with a surplus of heat that encourages models to find an extra source. Microwave eyes find compositional contrasts that linger in depth, as if mixing were hindered by steps. Gravity responds to flows that might be trapped between layers. The story grows stronger not by a single announcement, but by agreement across measures that do not know each other's language. Chemistry speaks. Heat flow answers. Fields and tugs nod in sympathy. Laboratories on Earth have begun to meet the required pressures and temperatures for moments in time. Diamond anvils squeeze tiny samples until they taste megabars. Shock waves from lasers or projectiles drive hydrogen and helium into the right corners of phase space long enough to measure reflectivity and miscibility. Quantum simulations run on machines that hum all night, predicting when and where the two lightest elements will part company. Results differ in detail but agree in outline. There exists a regime where helium prefers itself. There exists a slope in the phase diagram that lets droplets form. There exists a room in the planet where rain falls without clouds and darkness lights the clock. He finds elegance in the consequences for chemistry higher up. If helium is scarce near the visible atmosphere, the collision rates among molecules change slightly, and the balance of infrared cooling lines shifts by a trace. Ammonia, methane, and water carry the burden of radiative exchange with subtly altered partners. The effect is modest, yet in a system that integrates small differences over great areas and long times, even modest shifts matter. Colors adjust by a shade, cloud decks rise or fall by a few kilometers. Lightning counts drift with the ease or difficulty of building charge separation in towers that climb through helium-poor air. There is no thunder in this rain, no windowpane music, no smell before it starts. There is only patience and the certainty of gravity. The droplets gather in silence, let go, and warm the path as they descend. They escort neon to lower realms, build a layer that challenges convection, and feed the slow lantern that keeps the world bright. A planet can hide its secrets behind clouds, yet sometimes the secret is a simple act done out of sight for a very long time. Helium falls, and in falling it writes a second weather that chooses the pace of the first. He follows hydrogen into a depth where names begin to slip. At the top, it is a light gas that carries frost and colour. Far below it forgets how to be a molecule. Bonds loosen under the insistence of pressure. Electrons that once kept to pairs begin to wander. The fluid grows opaque. Reflectivity rises as if a mirror had been poured from nothing. In that realm, hydrogen behaves like a metal, not because of a lattice of atoms in a crystalline cage, but because electrons move freely enough to conduct, to feel fields, to carry currents through a substance that is still a liquid. It is an ocean without a shore, spread in a shell around a blurred heart, and it answers to magnetism like weather answers to wind. The transition is not a neat flaw. Temperature and pressure climb together along curves that thread phase space, and the boundary between molecular and metallic character may be a smooth crossover rather than a sudden step. In parts of that boundary, the fluid is a strange hybrid. Some regions hold remnants of two atom bonds, others host free electrons that scatter like sparks in dark water. Compressibility changes with depth. Heat capacity adjusts. Each of those shifts sets the stage for how the fluid will move, how it will carry energy, how it will fold itself into rolls and sheets that can sustain a magnetic field. A dynamo requires three simple things: conductivity, motion, and rotation. The first provides a way for electrical currents to exist without dying instantly. The second stirs those currents into patterns that can reinforce magnetic loops. The third adds organization, selecting spiral alignments that do not cancel as quickly as they form. In this ocean, all three are lavishly supplied. Conductivity rises by orders of magnitude once electrons are free to roam. Convection churns because heat wants to climb, and composition gradients push back imperfectly. Rotation with a period of hours turns the churning into columns that align with the spin axis. Within those columns, tiny fields grow and feed on larger motions until a planetary-scale magnetism emerges. The result is not a tidy dipole that points north and south with textbook symmetry. Measurements near the planet show patches and folds, a magnetism that prefers certain longitudes, a dipole that seems displaced, and a set of belts where the field intensifies like ridges in an underwater range. The ocean is not smooth. Heat enters it unevenly from below and leaves it unevenly above. Composition may vary in narrow layers set by rain of helium or gradients of heavy elements. Flow responds to those subtleties. Where convection is stronger, the dynamo beats more vigorously. Where convection is restrained, the field weakens or twists. The map that results is a collage, a living pattern that adjusts as the ocean trades heat with what surrounds it. Currents in the metallic sea feel resistance as heat. That resistance is not small. When flows wind lines of magnetic field, the field pushes back. The push appears as Lorentz force. The force extracts energy from motion and dumps it as thermal power. In a slow world that might be a footnote, in a giant, the accounting matters. The feedback can throttle jets that try to intrude too deeply, shaping how far atmospheric winds can reach into conducting layers. It can also alter the vigor of convection within the sea itself by converting kinetic energy into heat that modifies buoyancy. A hidden dialogue follows. Flow strengthens and twists field. Field resists and warms fluid. Warmth reorganizes flow. The outcome is a steady state that is never truly still. Within the ocean, waves carry information faster than a storm could. Alfvén waves run along magnetic lines like plucked strings, transporting momentum and stress. If a shear builds in one region, those waves can redistribute it across surprising distance. Magneto-inertial waves mix the language of rotation with the language of field, weaving patterns that process and modulate. In a conductive fluid, the speed of such waves depends on both density and field strength. That dependence writes a secret geography into the sea. There are corridors where signals sprint and basins where they loiter. Currents navigate that geography the way winds navigate mountain passes on Earth. Except here, the mountains are gradients in an invisible field and the passes are minima in magnetic tension. He sees bright scars near the poles when he looks through the planet's glow in ultraviolet and infrared. Each auroral arc connects to a tract of field lines that thread the metallic sea. The arcs brighten and dim with a supply of plasma and with the drag of rotation on that plasma. Energy flows along the lines, dives into the atmosphere, and then closes through currents that return to the ocean as stress. The entire magnetosphere is a haloed extension of the sea's mood. When the ocean's field strengthens in a sector, auroral curtains respond. When the ocean's circulation shifts, the distribution of radio bursts adjusts. The coupling is a circuit that spans from midnight space to the dark, high-pressure interior. He listens for the echo of composition in the ocean's behavior. If helium-enriched layers perch above the metallic realm, they change the insulation, reshaping how heat exits the sea. That reshaping can create regional contrasts in convective vigor. Heavy elements dissolved from a fuzzy heart may leak upward and alter density gradients from below, seeding regions less or more prone to overturn. In some patches, the sea might host double diffusive staircases where heat passes more willingly than materials do, resulting in thin convective layers separated by quiescent sheets. In others, full-throated convection might erupt and drive the dynamo more boldly. The result is a quilt of regimes stitched together by rotation and electromagnetic tension. Laboratories on Earth have pushed hydrogen to pressures where reflectivity spikes and resistance plummets. Tiny samples flare into metallic behavior for microseconds under shock, or hold it longer under diamond anvils warmed with lasers. Data is still sparse. Yet even with imperfect knowledge, the key properties align. The fluid can conduct. Its viscosity is low enough to permit turbulence. Its equation of state allows density variations that buoyancy can exploit. Under rotation, such a fluid builds helices that favor the constructive winding of field lines. The underlying physics is not fragile. It asks only that pressure-free electrons and that motion be allowed to persist. He imagines the boundary between molecular and metallic realms as a storm front that never migrates far in a day, yet drifts on the timescale of the planet's cooling. Above the front, lightning crackles in towers that burn with water and ammonia. Below the front, currents coil into loops that never flash, because their light is radio and their language is magnetism. The front is porous to heat but resistant to mixing of composition. It lets plume tips deliver warmth into the sea, then shears those tips into filaments that feed the rolls below. It receives upward tongues of metallic flow that surrender momentum and detach, becoming eddies that die as they lose conductivity. The interface is a teacher of patience. It allows exchange without surrendering identity. Jets that command the cloud tops cast long shadows into the interior. Where they graze the metallic realm, their shears become targets for magnetic drag. A deep-reaching jet can leave a fingerprint in the field map, a subtle modulation that aligns with certain latitudes. If the jet is shallower, the fingerprint fades. In this way, the magnetic ocean keeps an account of how far the visible engine intrudes. Flow that remains in non-conducting layers escapes the ocean's discipline. Flow that trespasses into conducting depths learns to compromise. The compromise sets a practical boundary between weather and dynamo, not a geometric surface, but a reach where electrons begin to make their authority known. He considers the ocean's age. It was born when the world's contraction and heating drove hydrogen into a state only hinted at in theory. Since then it has cooled and thickened, and its top has climbed or fallen as the balance of temperature and pressure wandered along slow curves. As it evolves, the magnetic field must evolve with it. Patches wax or wane. The displaced center shifts. Regions of high flux anchor and then slowly migrate. The planet's story of time is recorded not only in craters on moons and in scars of impact seen by telescopes, but also in the texture of a field that owes every curl to motions in a sea that no eye can visit. In that sea, electrons are the travelers and field lines, the roads. Heat is the currency. Rotation is the law. The map changes in detail while the rules remain simple. Conductivity allows memory. Convection writes that memory into space. The spin grants coherence to that writing. Out of these elements rises a magnetic world that surrounds the planet with a shield and a song. The song is measurable in radio arcs and auroral gleams. The shield is visible in the way plasma is sculpted, and astonished spacecraft are buffeted. Both are performances given by a liquid that thinks like a metal and moves like a storm. What waits further down may be a reservoir of heavier elements, a region of gradients where rock and ice have blurred into a muddy flame. The ocean wraps that reservoir and takes instruction from its temperature and its composition. The link goes both ways. Currents sculpt how heat escapes the fuzzy heart. The heart biases where currents will be strongest. The entire interior is therefore a feedback loop written in pressure and charge. A single fluid becomes a kingdom of roles, and one of those roles is to be a conductor for the world's invisible fire. He imagines a descent through warmth that never cools, and pressure that never forgives, until the idea of a floor becomes less persuasive than the idea of a blur. At the center of the giant, rock and ice do not sit like a mountain in a sea. They soften into possibility. Boundaries that seem firm in smaller worlds begin to act like gradients. The heart is not a kernel set apart. It is a volume where heavy elements grow more common as depth increases, a fog of weight rather than a pebble of certainty. The term that fits is simple and unsettling. The heart is fuzzy. In that interior, chemistry is a word that has learned new verbs. Water does not keep to liquid or solid. It becomes ionic and then superionic, a lattice where oxygen holds places while hydrogen tunnels through like lightning with memory. Silicates, carbon compounds, and ices unwind into species that chemistry at the surface cannot practice. Metallic hydrogen, thick and hot, welcomes some of these into solution. Others become suspensions that stir and settle with time. The result is not a clean border where rock ends and hydrogen begins. It is a transition tens of thousands of kilometers wide, where concentration rises and falls in slopes and steps. The weight of the planet presses until numbers lose their homely feel. Millions of atmospheres become the grammar. Temperatures rise into thousands of degrees. Under such insistence, the solubility of heavy elements in hydrogen grows generous. What might have been a solid core in a younger planet can begin to dissolve. The process has no drama. There are no cracks to hear, no landslides to witness. There is only the quiet drift of atoms from a concentrated center into a surrounding fluid that accepts them. Convection carries some of that drift upward, until composition itself begins to resist, because the heavy makes parcels denser and discourages their rise. The heart blurs into layers that allow heat to creep while keeping elements mostly where gravity prefers them. He considers a thought experiment. Drop a shard of rocky material into metallic hydrogen at the conditions of the deep interior. The shard warms. Bonds relax. Atoms leave their lattice and join the crowd. The shard forgets it was once a piece of a world. Multiply the experiment by 100 billion fragments, each the gift of accreted planetesimals or the residue of a primordial concentration. Time stretches across eons. The fuzz is born, not as a neat shell, but as a region of gentle but persistent enrichment, a place where the mix tilts toward oxygen and silicon and carbon, ingredients that instruments might infer only by how they alter the shape of the gravitational field. The gravity field does keep the secret imperfectly. Mass distributed in a gradient tugs differently than mass tucked into a compact nugget. Harmonics of the planet's pull adjust by trace amounts. With careful measurement, those traces become evidence for a center that is neither sharp nor empty. Models that try to pack all heavy elements into a small radius fail to match the tug. Models that dissolve everything evenly into the envelope fail as well. The best portraits place tens of Earth masses of metals and ices into a broad region that shades from rich to richer as the radius shrinks, a watercolor rather than a line drawing. Thermal logic enters quietly. A fuzzy heart conducts and convects heat differently than a crisp one. If heavy elements are spread through a volume, they raise the average molecular weight of fluid there. Buoyancy responds. Rising parcels that lose a little heat also lose a little compositional privilege and sink back. Descending parcels that carry slightly more metals become heavier still and continue down. The result is a stratification that offers resistance to large overturning motions. Heat must travel by slower routes, by diffusion and by small layered cells that exchange warmth without trading as much composition. The heart becomes not only fuzzy in makeup, but also patient in its cooling, a timekeeper that stretches the planet's luminous youth. He remembers that erosion works both toward disorder and renewed order. If a concentrated center begins to melt into its surroundings, the surroundings can carry some of that material outward until resistance stiffens the flow. Layers can then establish themselves spontaneously. Each layer has a distinct mix and a distinct temperature. Interfaces between layers act like mirrors for motion, reflecting plumes that try to cross. In some epochs, the mirrors allow a little passage. In others, they are polished and strict. The heart learns to speak in staircases rather than in cliffs. Each step helps support the weight above while hoarding a fraction of the heat below. Impacts may have left their handwriting on this blur. A large body striking early in the planet's life could have dumped energy deep within, mixing heavy material outward and upsetting any compact structure that had begun to form. After the chaos cooled, gravity would have started the slow work of sorting again. What remained would be a heart that never resharpened, because solubility and slow mixing kept gradients soft. Even without such an event, the simple act of swallowing a rain of planetesimals during growth would have produced a similar fate. Bits dissolved at depths set by their melting curves and by the state of hydrogen at the time of entry, painting the nascent heart with streaks that later spread. He listens for how such a heart changes the music of the planet. Sound waves in a stratified interior reflect and refract where gradients live. Normal modes depend on compressibility and on how density increases with depth. A fuzzy center creates a spectrum subtly different from that of a crisp core. In principle, those differences could be heard in tiny vibrations that a patient observer might catch. In practice, they remain hints. Gravity has spoken more clearly so far. Magnetism, too, may answer indirectly, since heat delivery from below sets the vigor of the metallic ocean that wraps the heart. Where gradients slow the flow of energy upward, the dynamo might wax or wane in response. Materials in this realm have personalities that seem invented. Water, under these forces, can take on a superionic state where hydrogen moves through a crystalline maze of oxygen as if it were a liquid inside a solid. Ammonia can join and distort those lattices. Silicates can break into ions that wander. Each change modifies opacity, heat capacity, and the way the fluid responds to compression. The heavy elements are not mere ballast. They are active contributors to the equation of state, the rule book that decides how gravity, pressure, and temperature play with one another. The rule book has many pages that are still blank, and yet the overall story points to a heart that is less a boulder and more a fog that knows how to bear weight. He draws a map in his mind that has no roads, only contours of concentration. At the very center, enrichment is strongest. Outward from that, contours relax. Then comes the metallic sea, where hydrogen conducts and rolls, still seeded with heavy species that thin with radius. Above that lies molecular hydrogen and helium with traces of condensables, the realm where storms write colour. The boundaries between these realms are not sharp, and that very lack of sharpness is the signature. In a compact core model, a single radius would announce itself by how gravity changes. In this portrait, the change is gradual, and the tug fades as a sigh rather than as a step. Time works on the heart the way a river works on clay. Cooling shifts the depths where certain phases are favoured. Solubilities evolve. Layers thicken or thin. The rate at which heavy elements can leak outward adjusts. If helium rain is occurring above, it can build a compositional barrier that slows exchange between the metallic sea and the heart beneath. If deep convection strengthens, it can nibble at the edges of gradients and soften them slightly. The fuzz records these eras as a slow palimpsest. Each epoch writes over the last without quite erasing it. He wonders how the heart began, whether a small seed drew gas out of the young nebula, or whether gas first gathered and then invited solids into dissolution, is a question that echoes in the present structure. A heart that started crisp but dissolved would naturally produce gradients that extend far into the metallic realm. A heart that began diffuse would settle into slopes more readily. In both scenarios, the result today can look similar, but the history embedded in the exact profile is different. Instruments can only see integrals and harmonics, never the path that led to them. The fuzz invites humility. It keeps origin possible without surrendering to a single tale. The picture that emerges is not a compromise in the pejorative sense. It is an achievement of physics. Under enormous pressure and relentless heat, matter chooses gradients because gradients satisfy many constraints at once. They conserve energy, minimize instability, and respect the way solubility changes with depth. A sharp heart would be a violation of these pressures. A void would be absurd. Between these extremes lies a centre that is neither firm nor empty, one that gives the planet both inertia and adaptability. He leaves the thought with an image of weight that behaves like weather. The heart breathes slowly through conduction and through small convective steps. It feeds heat to the metallic sea while it coddles elements that prefer to rest deep. It influences gravity subtly and magnetism indirectly. It holds the memory of impacts and of accretion. It is not a secret stone. It is a gradient written into space by pressure and time, a quiet core that teaches that even certainty can be a slope. He studies a staircase that no eye can see. It rises through depths where pressure makes chemistry deliberate and heat impatient. Each step is a thin convective layer. Each riser is a quiet interface where composition changes more readily than temperature, or temperature relaxes more willingly than composition. The contrast between these diffusivities writes the architecture. Heat slips through molecules like rumour. Heavy elements move with reluctance, bound by inertia and by the cost of mixing against gravity. Where heat outruns material transport, fluid organizes itself into stacks. The result is double diffusion, a choreography in which two gradients, each stable alone, conspire to create motion when paired. In small classrooms, the tale begins with a pot on a stove. Warmth rises, cool sinks, and a roll fills the volume. In the deep of a giant, the recipe has an extra ingredient. The fluid is salted not with sodium but with a surplus of heavy elements, or with helium that prefers depth. That compositional gradient makes the fluid stable in a way simple heating cannot undo. A parcel that lifts brings its heavy mix with it and remains dense even as it warms. A parcel that descends lightens as it cools and refuses to continue. Large overturning is deterred. Yet nature abhors a bottleneck. Heat still wants out, and composition still wants to stay put. The compromise is a ladder. Within each step the fluid overturns locally. Small convective cells form and shuttle warmth upward and coolness downward with vigour. They stop at the riser, where the gradient of composition guards the boundary like a customs gate. At that gate, heat can pay the toll quickly by conduction and radiation. Heavy elements must negotiate slowly, molecule by molecule. The mismatch produces a thin layer where temperature smooths while composition hardly budges. That mismatch is where stability is manufactured. It is also where the next step is invited into existence, as the contrast above and below sharpens until new overturning can bloom again in the layer that received more heat than mass. He turns to the rules that decide when such ladders appear. Gravity, temperature gradient, composition gradient, and diffusivities set the stage. If a fluid is superadiabatic in temperature, pure heat would produce convection. If, at the same time, a background increase in mean molecular weight with depth exists, composition tries to forbid the overturn. The two influences combine in the Ledoux criterion. When temperature destabilizes, but not enough to overwhelm the stabilizing composition, the verdict is double diffusive instability. The unstable state does not tumble into chaos. It calcifies into order. Order, in this realm, is a stack of thin convective sheets separated by diffusive membranes. He recognizes the family resemblance to another ocean. In Earth's seas, warm, salty water lying over cooler, fresher water can organize into steps. There the roles of heat and salt trade names, but the logic is the same. The upper ocean builds staircases that extend for kilometers, each step mixing vigorously while respecting a sharp salinity jump at its top and bottom. The pattern persists until external forcing erodes the contrasts or an intrusion triggers reorganization. The giant's interior is a cousin written in hydrogen and helium. Heavy elements make the salinity. Internal heat is the stove below. Pressure magnifies the discipline of the layers. The scale is planetary, but the physics remains intimate. He imagines how a staircase changes the journey of energy. In a fully mixed shell, convection is a fast highway. Heat rises in plumes, expands, cools, and deposits its cargo into space with efficiency. In a stack of steps, the highway breaks into short switchbacks. Each convective layer transports heat swiftly over its own thickness, then hands it off painfully slowly across the diffusive interface. The overall flux drops. Cooling slows. The interior remains warmer for longer. The effect is not cosmetic. It retunes the planet's evolution, prolongs internal luminosity, and alters the vigor of the metallic sea that lies below, because the throttle on heat affects the roles that wind magnetic fields. He considers how a staircase might be born. A primordial rain of heavy material during formation can leave a gentle gradient with depth. Later, dissolution of a fuzzy heart can continue to feed that gradient from below. Independently, helium that separates at depth and falls can add compositional contrasts that reinforce the barriers. Introduce a steady upward heat flow, and the recipe is complete. The fluid seeks a state that lets heat pass, but keeps composition sorted. It tries uniformity and fails. It discovers a single broad overturn, and finds it too costly in potential energy. Finally, it fractures into many layers, each just thick enough that buoyancy overcomes viscosity within, but thin enough that the contrast across boundaries remains protective. Turbulence does not end the arrangement. It inhabits the steps rather than demolishing them. In each convective sheet, eddies, churn, and merge until they meet the interface. There, shear can strip wisps of the interface's material, but the stabilization by composition and the rapid diffusion of heat rebuild the barrier after each nibble. Occasionally a strong event breaks through, allowing a pulse of composition to escape or to invade. That pulse changes densities in the neighboring layer, which can trigger the birth or death of steps. The staircase is not a static sculpture. It is a living architecture that grows, splits, and heals while maintaining its overall purpose of throttling exchange. He asks what signature such layering might leave for a patient listener. Thermal gradients would be steeper than in a fully convecting region, so the brightness of microwave emission passing through certain depths would adjust subtly. Gravity harmonics might shift if winds are trapped within or between layers, because mass would be rearranged along corrugated paths rather than smeared evenly. Magnetic behavior could respond if heat is fed into the conducting sea beneath in patches or pulses rather than uniformly, because regions of stronger convection would wax and wane. Even cloud-level chemistry might feel the distant echo, as slow delivery of deep volatiles modulates the background against which storms work. He sketches a profile of mean molecular weight with respect to radius. It rises downward in a soft slope, then shows small steps, each a few kilometers to hundreds of kilometers thick. Overlaid is a temperature profile that rises quickly in the rises and more gently across the steps. Superposed again is a schematic of tiny overturning arrows within each step. The whole picture looks like a ladder drawn by a patient hand. The distances dwarf continents, yet the controlling physics experiment could be held between diamond tips in a lab, where a fluid mixture warmed from below and salted from above spontaneously organizes into stacked convection with diffusive sheets between. A question gnaws at the edges of the map. How long can such order endure amid a world of shear, waves, and intrusions? The answer is not a single number. Ladders in some realms may be robust for millennia, fed by steady gradients and protected by the very barriers they create. In other regions, waves from above or below can thicken interfaces until they merge, erasing steps and inviting a phase of freer convection. Then, as gradients rebuild, the ladder can re-emerge. The rhythm is slow compared to weather, fast compared to planetary ages. It is a tempo set by diffusion coefficients and by the background supply of heat and heavy elements. He returns to the microscopic cause of the macroscopic grace. Thermal diffusion is quick, because energy lives in motions of light particles and in vibrations that can be passed along rapidly. Compositional diffusion is slow because it demands rearrangement of identities, a literal change in what the parcel is made of. In a multi-component fluid under pressure, that rearrangement is costly. The universe chooses the cheaper path while obeying conservation. It builds layers that allow the quick to pass and the heavy to pause. The build is not an exception to disorder. It is a higher order born from the competition of processes that refuse to share a timescale. He listens for the story told by a single step. Warmth arrives at its base, conducted through a riser below. The layer begins to overturn, lifting heat upward and dropping slightly cooler material downward. As it works, its top interface warms enough that some of the stabilizing density contrast is eroded. The layer thickens until it encounters the next riser, where the composition again stiffens the flow. Small intrusions sneak across, bringing a whisper of heavy elements upward or a hint of lighter mixture downward. Over time, those whispers accumulate, and the positions of interfaces drift. The staircase migrates, not as a rigid frame, but like dunes reshaped by a wind that never stops. He considers a grand implication. If ladders are common, then the interior remembers not only initial conditions, but also the sequence in which layers formed and merged. The fossil record of gradients is not erased completely by convection. It is edited. Traces persist in the exact thicknesses and spacings of steps, in the direction and strength of trapped jets, in the distribution of heat flux that feeds the conducting sea. Any attempt to reconstruct the path of the world through phase space will have to read that record. The reading will not be simple. It will be worth the difficulty, because a ladder is not just a transport mechanism. It is a diary written in buoyancy. He leaves the staircase with a sense of constructive restraint. The layers are not barriers meant to frustrate knowledge. They are solutions to the planet's need to move heat while honoring the weight of its heavy species. They keep order where chaos would be wasteful. They let motion flourish where it pays and forbid it where it would cost too much in potential energy. A giant can afford patience. It spends that patience in steps of double diffusion, each one a small agreement between heat eager to flee and composition content to stay. Together, those agreements build a ladder tall enough to touch the weather above and sturdy enough to lean on the metallic seas below. He studies lines of wind that behave like architecture. They encircle the planet in alternating bands, eastward, westward, eastward again, each a river confined to its latitude. At the cloud tops, the speeds are printed in colour, measurable by the drift of small features as they ride the belts. But the question that matters hides beneath the beauty. How far do these jets descend before they surrender to the weight of pressure? The the pull of magnetism, the discipline of deeper layers. To answer, he listens not with eyes, but with gravity. A spacecraft passes close, again and again, and each pass is a weighing. The path bends by tiny amounts as it skims the giant, and those bends are encoded in the Doppler beat of radio waves reaching home. The planet's mass is enormous, yet the deviations from a perfect sphere matter. From the sea of numbers emerge coefficients with quiet names. Some belong to symmetries set by rotation and bulge. Others, the odd ones, whisper of flows that do not balance north against south. Those odd harmonics are fingerprints of winds that carry mass sideways and downward, creating density contrasts where a static world would be smoother. He reads them like the bars of a score. They tell him the jets are not painted on. They have depth. The depth is not infinite. Inversions of the gravity field suggest that the strongest bands claw downward for thousands of kilometers before fading. The fade is not an abrupt wall. It is a decay that can be written as a scale height of momentum, a measure of how the shear weakens with pressure. If the decay were shallow, the odd harmonics would be slight. They are not. If the decay were bottomless, the harmonics would overshoot. They do not. The middle answer is the truth. A realm where weather retains its identity far beyond the cloud deck, then hands it off to physics that prefers quiet. He frames the problem in balances beloved by rotating fluids. At the top, geostrophy rules, a truce between pressure gradients and the Coriolis influence. Vertical structure is guided by thermal wind balance, in which horizontal temperature contrasts demand shear with height. In a giant, those contrasts are small, yet over planetary distances they accumulate into significant speed differences. Deeper down, as density climbs and conductivity hints at its approach, other actors enter. Shear meets drag from currents induced in conductive layers. The drag converts motion into heat with the efficiency of a brake that never wears out. The result is a practical boundary between meteorology and magnetism, set not by a surface but by a competition of timescales. He imagines a meridional slice through one jet, a cylinder of flow coaxed by rotation into aligning with the spin axis. In such a world, motions prefer columns rather than slabs. The arithmetic of a rapid day enforces it. The column narrows toward the poles, widens toward the equator, and carries momentum like a conveyor hidden behind the visible band. Within the column, parcels move along paths that barely tilt with depth for a long reach. Then, at a certain pressure, the background acquires a charge. Electrons roam more freely, and magnetic fields stretched by the flow push back. The column feels the resistance. Shear softens. The current generation rate falls. The cylinder's base frays into eddies that do not last. A different line of evidence complements the weighing. Microwave eyes, tuned to wavelengths that pass through upper clouds, find contrasts in absorbers that ride with the flow. Where a jet descends, it carries its chemical personality downward. Where it weakens, that personality diffuses into anonymity. The brightness against latitude, when compared with gravity's odd notes, sketches a consistent portrait. Deep jets plunge by thousands of kilometers under mid-latitudes and fade more quickly near the poles. The equator remains a world apart, driven by waves that prefer that corridor, boasting a fast eastward stream that may reach the deepest among the weathering winds. He turns to momentum budgets. Any wind that persists in depth must borrow angular momentum from somewhere and repay it elsewhere. At the top, eddies generated by baroclinic instabilities move momentum across latitudes. Deeper, the jets must either tap rotational energy by subtle torques, or accept delivery from patterns of slow overturning that carry spin like freight. The book must balance. If magnetic drag is strong at a certain depth, then the jets can afford to be bowled above it. They spend their speed where drag is weak, and slow their march where electrons are waiting. The result is a staircase of momentum itself, a profile with generous space for motion, and below a region of penance. He watches for asymmetry, because a world this dynamic rarely shares perfectly between hemispheres. The weighing finds that some odd harmonics carry phases that favor one side's jets by small but telling amounts. That favor may come from differences in deep temperature, from curls in the magnetic field that are not evenly distributed, or from long-living storms that torque the bands nearby. The jets, though global, answer to local conditions in depth. They are a choir singing the same hymn while standing on slightly different steps. Equations make promises that nature modifies. The Taylor column ideal says deep flows should be coaxed into cylinders parallel to the spin axis. Observations hint that the promise holds in part and fails in detail. Where stratification is strong, columns can be tilted. Where composition changes in thin sheets, columns can be segmented. The deep jets then resemble braided ropes rather than single cords. And the braiding matters. Braids resist shear differently and couple to their surroundings with a spectrum of timescales. Gravity harmonics integrate over them all, so the inversion gives one answer for many strands. He admires the humility in that process. The planet is generous with clues but demands inference. He asks what such depth means for weather's identity. If a jet reaches far below, the storms that ride it can draw upon reservoirs of momentum and heat unavailable to shallow systems. Their lifetimes lengthen. Their interactions with neighbours take on the character of tectonics rather than rainfall. Conversely, if a jet's route is shallow, variability at the top becomes freer, more jittery, swayed by transient forcing and quicker to forget. The map of depths becomes a map of memory, and the belts with the deepest reach are the historians. They keep records of internal heat flux and past wave activity in the distribution of speed with pressure. A limit lurks in the arithmetic of conductivity. The deeper a jet trespasses, the larger the electric currents it induces, and the stronger the back reaction. That back reaction appears as ohmic heating and as braking. If the heating were too large, it would exceed the measured internal flux. It does not. Therefore, the trespass has a ceiling. This constraint, born in the language of energy, agrees with the constraints born in gravity's language. Each says that jets fade well before reaching the hottest conducting layers, but not before leaving clear fingerprints in the field felt by a passing machine. He brings in waves with long patience. Rossby waves ride the jets, trading vorticity with them, and shepherding momentum along arcs that wrap the planet. Some of those waves can burrow deeper than others, depending on how stratified the layers are. Those that dive can help carry the imprint of top weather into the lower reaches, while those that skim give near-surface storms more to do. In this way, the spectrum of waves becomes a spectrum of depth couplings. A band fed by deep-reaching waves will have a different character than a band starved of them. He imagines an experiment with dye that could never be done. If one could tag air at the cloud tops with a tracer and return years later to sample at depth, the tracer would be found far below in some jets but not in others. The vertical reach of transport would mirror the gravimetric inversions, and the patterns would show that the boundary between atmosphere and interior is not a wall but a negotiation. The negotiation has clauses written by rotation, by heat, by composition, and by the quiet law of electromagnetism rising from below. He listens again to the radio heartbeat of the spacecraft as it loops by, and he understands why each pass is different. Tides from moons pull a little here, a little there. Jets shift shape by a fraction. Polar cyclones rearrange their dances. The odd harmonics breathe. Time averages smooth the roughness, but the roughness itself is a message. Deep winds are alive, not carved stone. They change on schedules longer than storms but shorter than ages, nudged by energy drifts and by the reweaving of layers underneath. The riddle that remains is both precise and poetic. Where does weather end and interior begin if winds carry identity thousands of kilometers down? The most honest answer is a region rather than a boundary, a band of depth where the character of flow changes from choices made by buoyancy and rotation to choices made by conductivity and field. Above, colour and cloud convert heat into motion. Below, motion accepts discipline from charge. Between, the jets fade like music walking away, still audible, still itself, and then the sound is taken up by another instrument that plays a deeper register. He turns back the clock to a nebula lit from within by newborn heat and trimmed by starlight from beyond. Dust and gas swirl in a flattened disk, a slow river of hydrogen and helium laced with grains colder than most words allow. The disk is not quiet. Spiral arms flex under their own gravity. Shocks heat narrow ribs. Snowlines carve chemistry into rings. Nearest to the sun, rock survives while ices sublimate. Farther out, water freezes. Farther still, carbon monoxide and nitrogen settle as frost. In this workshop, a giant must be built before the gas disperses. Time is the most severe tool. It grants only a few million years. Two ideas volunteer to assemble such a world. One is patient, the other is abrupt. The patient vision begins with pebbles, centimetre-scale stones that drift inward because gas drags them. Where a growing embryo sits, pebbles do not pass unmolested. They spiral into its gravity well and join the body with startling efficiency. This is pebble accretion. The embryo fattens into a core measured in earth masses and then approaches a threshold called the pebble isolation mass. At that point, its gravity carves a pressure bump in the gas that blocks further pebble drift. The core's appetite changes diet. It begins to bind a gaseous envelope that cools, contracts, and beckons more gas. If conditions hold, the envelope crosses a tipping point where self-gravity takes command and the growth runs away. Hydrogen and helium answer the call, and a giant is born. The abrupt vision asks the disk itself to collaborate. If the gas is heavy enough and cool enough, it fragments into clumps under its own weight. Each clump contracts and can, in principle, become a giant without the long wait for core assembly. This is disk instability. The obstacle is survival. Shocks shear clumps. Radiation leaks their heat. Migration toward the star can be swift. The clump must accrete and shrink faster than the forces that would dissolve it. In some disks, the recipe is favorable. In others, not. The universe may prefer the patient route more often, reserving the abrupt path for rare, massive, and cold circumstances. He listens to the tally of heavy elements, because that tally judges the builders. A giant gathered mostly from gas should carry only a small fraction of metals compared with the star. A giant raised by pebbles and planetesimals before drinking gas should carry more. The numbers measured today favour richness. Tens of Earth masses of heavier species reside inside, blended into gradients that refuse a sharp core. Noble gases appear too abundant to be explained by warm capture alone, as if the building blocks were colder than the asteroid belt. The verdict leans toward a core nurtured by solids, then remodelled as gas arrived and time dissolved boundaries into fuzz. Pebbles supply speed. They drift through the disk on orbits slowed by pressure-supported gas, delivering material to any embryo that reaches out with gravity. As the embryo grows, it warms nearby gas and stirs turbulence that can either help or hinder further delivery. If growth is quick enough to reach pebble isolation while the disk still holds its mass, the door opens to gas capture. That moment is delicate. The envelope must cool to contract, and cooling depends on the opacities set by dust grains entrained in the gas. Too many grains and the envelope insulates itself, delaying contraction. Too few and cooling races ahead. In between lies a corridor wide enough for a giant to form before stellar winds and ultraviolet light peel the disk away. Planetesimals retain a role even in a pebble world. Meter-scale to kilometre-scale bodies can deliver bursts of heavy elements and stir the envelope with energy when they plunge into it. They also sculpt the feeding zone, colliding and fragmenting, creating fresh pebbles and swallowing others. Their bombardment can spike the metallicity of the growing giant at particular times, leaving imprints in the interior as layers or gradients. In that sense, formation is not a single process but a braid. Pebbles lay the foundation, planetesimals spike the mix, gas smooths edges into a planet, and then slow chemistry in depth completes the edit. He watches migration with suspicion and gratitude, because without movement a giant might not find the materials it carries now. A growing planet interacts with the disk and feels torques that urge it to drift. Small cores slide inward in Type I migration, fast enough to threaten doom if no rescue arrives. Yet the very growth that pebbles provide can reach a mass where the planet opens a partial gap. The migration slows and morphs into Type II, coupled to the viscous evolution of the disk. Some scenarios propose a dramatic journey, a tack inward that carries the young giant close to the Sun before a reversal and retreat. Such a detour rearranges the inner system, scattering material, starving some zones while feeding others. The fingerprints of that rearrangement linger in the architecture of smaller worlds. Whether the giant that concerns him travelled far or stayed near its present orbit, the disk wrote its itinerary in spirals and wakes. A different heartbeat in the nursery is the star itself. Young suns flare. They blow winds that erode disks and carve holes. Ultraviolet light photoevaporates gas from the top down. A forming giant must therefore race. The outer layers need to contract in time. The envelope's heat must escape. If helium rain in later ages slows cooling, that is a luxury granted after birth. During assembly, the lantern must be bright and efficient enough to turn mass into gravity's captive. It is a drama with a firm third act. The curtain falls on gas within a few million years. Any world that misses its cues will remain a dwarf of rock and ice. He recalls that capture is only part of the heritage. The composition of the building blocks imprints the final mix. If pebbles drifted in from beyond the water snow line, they were ice-rich and delivered oxygen by the bale. If they came from even colder rings where carbon monoxide freezes, they were laden with carbon and nitrogen. The timing of accretion relative to the migration of these snow lines matters. As the disk evolves, temperature fronts move. A core that begins just beyond water's line may be fed mostly water ice and rock. A core that grows later or farther out may sip more carbon and nitrogen. These differences help explain the abundances seen in the present atmosphere, where methane, ammonia, and water are not mere accents but clues to birthplace and season. Impacts also volunteer as sculptors. A collision with another large embryo can inject heavy elements deep and distort the envelope. The shock can stir the heart and blur any nascent core while leaving asymmetries that may persist in gravity or magnetic data long after. In more gentle collisions, the visitor dissolves gradually, seeding the interior with metals that later diffuse. Either way, merger changes the script. It accelerates the pace toward a giant's mass while complicating the interior's profile, offering a natural path to a fuzzy heart. He allows the moons to add testimony. A giant that assembles gas forms a subdisk of its own, a circumplanetary disk where ices and dust condense into satellites. The composition gradient across those moons, richer in ice outward, suggests a local miniature of the nebulous snowlines during formation. The mass available in this subdisk, and the time it remains, depend on how rapidly the planet accreted and how it interacted with the surrounding nebula. Those constraints fold back into the main story. A planet that grew leisurely from pebbles would support a long-lived subdisk where moons could accrete in ordered sequences. A planet that collapsed in a fragment would present a different field of play, more sudden and less layered. The quiet order seen in the family of large satellites favours the measured growth that a core and pebbles provide. He listens to the calendar scratched by meteorites. The oldest solids in the system carry isotopic clocks that place the assembly of the first rocky seeds within a blink of astronomical time. By 1 to 3 million years, gas must already be disappearing from many disks. A giant formed by pebbles can meet that deadline, if pebble flux is high and if envelope cooling is not throttled by excess dust. Disk instability could in principle beat the clock, but the necessity for clump survival and the signatures of heavy element enrichment push the balance back toward the slower but steadier plan. Laboratories and telescopes add modern footnotes. Arrays on Earth image young stars with rings carved in their disks, gaps suggestive of newborn planets clearing paths. Spectra detect water vapor lines at temperatures and radii that map snow lines in situ. Models translate those images and lines into mass and timescale estimates, that align with a narrative where cores assemble in zones of generous pebbles, where migration is common but not always catastrophic, and where giants that survive do so by timing and by exploiting the physics of drag and heat. He lets the story condense. A giant like the one he contemplates likely began with a core that fed on inward drifting pebbles, reached the mass that dammed their river, and then captured gas while the disk still pooled around the young Sunday. It migrated some distance, perhaps far, perhaps modestly, sculpting inner architecture as it went. It accreted heavy elements both during growth and in later injections by planetesimals and peers. Its envelope contracted and warmed, later to reorganize under the patient rain of helium and the patient chemistry of high-pressure water and rock. The result is a world whose current interior keeps memory of its violent nursery as gradients rather than scars. Birth, in this reading, is not a single scene. It is an era where dust becomes stone. Stone becomes a magnet for pebbles. Pebbles hand off to gas. Gas invites migration. Migration invites encounters. And all of it happens under a sky that is itself changing as the star unfurls its first breaths. Out of that choreography emerges a planet large enough to govern a magnetosphere, to host a metallic ocean, to fold heat in ladders and shells. Its bands and storms are late poems written by an author forged quickly when the clock was stern. The nursery was not kind, only sufficient. It gave just enough time, just enough material, just enough calm between flares for a giant to take its shape and begin the long work of being. He watches hands coax planets from millimeters. Two diamonds face each other like patient mountains, their tips polished to a clarity that can bear the weight of worlds. Between them sits a speck of hydrogen, or a shard of water, or a whisper of helium sealed in a metal gasket. Screws turn. Pressure climbs until human metaphors lose their grip. At hundreds of gigapascals, bonds forget their loyalties. A ruby chip glows with laser light, its fluorescence shifting to announce the load. The microscope shows only a sliver of brilliance. The data recorder sees the birth of alien behavior. The diamond anvil cell is a small throne for great forces. It reaches deep pressures quietly, holds them long enough to measure properties carefully, and allows heating by infrared lasers that write dots of sun into the speck. In that chamber, hydrogen grows opaque and reflective. Resistance drops, a hint of metallic conduct. Raman lines wander, fade, and recur in new guises as molecules reorganize. Helium mixes until it does not. Water stiffens into a superionic phase where oxygen keeps a crystalline scaffold, while hydrogen runs through it like lightning trapped in glass. Each curve on a plot is a sentence in an unfamiliar language that begins to feel readable. Impulses bring a different grammar. Gas guns hurl projectiles that strike targets and launch shocks. Lasers focused on thin foils vaporize them into plasma that drives compression waves into samples. Pulsed power machines slam magnetic fields into metals and rebound them with violence measured in megabars. The shock lasts for microseconds, but in that heartbeat matter visits temperatures and pressures that instruments can trace. Street cameras watch, reflectivity rise. Pyrometers take the color of the glow and translate it into temperature. Velocity interferometers read the motion of a surface and recover the stress inside. With enough shots, a Hugoniot curve is drawn. It is a road through state space that matter must take when pushed hard and fast. Ramp compression tunes the violence. Instead of a single jump, the pressure rises in a smooth climb that can keep the sample cooler for the same ultimate load. That matters to hydrogen, which otherwise overheats along the classic shock path and skips the very states a giant planet favors. By precompressing hydrogen gently in a diamond cell, then sending a tailored ramp through it with a laser, researchers steer the sample onto adiabats that resemble the interiors. They measure reflectivity and conductivity along that path and find where electrons begin to roam. Metallization stops being a legend and becomes a set of coordinates. Mixtures tell more than pure elements. Hydrogen with a trace of helium reads like the deep envelope. Hydrogen with a little water or ammonia hints at the chemistry of mid-layers. In these blends, immiscibility lines can be mapped as places where textures appear, droplets form, or spectra split. Helium shows a preference for itself under certain conditions. Neon follows its friend. Water changes its role from a simple coolant to a carrier of ions that alter conductivity and opacity. These are not trifles of materials science. They are the knobs and levers that set how heat escapes, how ladders of convection form, and how a magnetic ocean winds its currents. A quiet revolution runs in parallel on cold machines that hum at night. Quantum simulations take first principles and teach them to speak under load. Density functional theory builds electrons into waves and asks them to choose where to dwell. Quantum Monte Carlo samples the possibilities more bluntly, trading speed for fidelity. Machine learning potentials, trained on these expensive truths, extend them to larger systems and longer times. From these calculations come equations of state that tell pressure from density and temperature, transport coefficients that reveal how fast heat walks and how quickly momentum smears, and phase maps that sketch where fluids conduct and where they resist. The predictions are not perfect, but they aim at domains experiments can only glance at. In laboratories, opacity becomes a tangible number. Small samples, held between diamonds or shocked into sparkle, reveal how they swallow and emit radiation. The values written down in those rooms migrate into models where they decide how deep starlight reaches and how readily interior glow finds its way out. If opacity rises in a layer, heat lingers and convection strengthens. If opacity falls, radiation carries more of the burden and the flow quiets. The stakes are planetary. The brightness seen in infrared telescopes and the vigor of the engine that drives belts and spots are both tuned by numbers born beside diamond anvils. Viscosity and electrical resistivity add their quiet signatures. A conducting fluid with low viscosity favors turbulence and efficient dynamos. Measure its resistivity at pressure, and one can calculate the magnetic Reynolds number that decides whether field lines are carried like leaves in a stream or shredded and diffused. Shocked hydrogen that reflects like a metal suggests that currents will not die instantly. Precompressed hydrogen that shows a gradual rise in reflectivity suggests that the transition to metallic behavior is a blur rather than a jump. Each nuance matters because a magnetic field that is patchy and displaced needs a conductor that is lively yet unevenly fed. The experiments also sketch the cost of mixing. Drop a grain of silicate into metallic hydrogen at pressure, and it dissolves in calculations that agree with hinting measurements. That solubility suggests that a crisp core will tend to smear. Dissolution is not uniform. Some species prefer more to stay than others, and that preference feeds gradients. The fuzzy heart is not only a poetic concession, it is a thermodynamic necessity recorded in phase boundaries and partition coefficients written in lab books with numbers that smell faintly of oil and ozone. There are frustrations that sharpen the work. Diamonds break under the most interesting loads. Samples slip out of the laser focus as they thin to nothing at the edges. Shocked hydrogen escapes its containment, and the diagnostic that would have recorded its conductance is blinded by a glare. Simulations disagree because two exchange correlation functionals whisper different advice to their electrons, yet each setback breeds method. Thicker culettes and better gaskets hold pressure more cleanly. Raman thermometry refines temperatures in cells heated by infrared spots. Laser pulse shapes sculpt ramps that avoid spurious shocks. Simulations combine many small boxes into a picture that resists the whims of any one approximation. Cross-checks matter more than applause. When a diamond cell claims a rise in reflectance with pressure, a shock shot must see the same trend at higher temperatures along a different path. When a simulation predicts an immiscible stripe for helium in hydrogen, a mixture in a gasket must fog at the same place and clear below it. When a ramp reports metallization at a certain pressure and temperature, the conductivity inferred from radio observations must fall within compatible ranges once the model folds in composition. Confidence grows not with a single spectacular number, but with many modest agreements. The edge of experiment is not only about maximum pressure, time also matters. A microsecond is long enough for electrons to find paths and for phonons to share heat. It is short for atoms to trade places across sharp composition gradients. A sustained load in a diamond cell is the reverse. Atoms can migrate, layers can ripen, but temperatures are harder to hold. Between these extremes lies a new art, maintaining intermediate times under gentle ramps so that diffusion has a chance to matter while shock heating does not overwhelm. Those regimes begin to speak directly to layered convection and to slow immiscible rain. He listens for lessons about uncertainty. The number on a figure may wear a neat error bar, but the true mistake is often one of interpretation. A rising reflectance could mean free electrons have appeared, or it could mean bound states are shifting in ways that mimic metallic behavior. A kink in a Hugoniot could announce a phase change, or it could be the fingerprint of chemistry tearing and reknitting bonds in an avalanche. The antidote is creativity beyond any single diagnostic. Combine reflectivity with direct conductivity. Combine both with sound speed, then overlay them with structural fingerprints from scattering. The more sense is brought to bear, the less likely the planet will be misread through laboratory glass. The work changes more than a few constants. It redraws the intuition for matter under load. Hydrogen is no longer a gas and a polite cryogenic liquid. It is an artist that paints mirrors out of pressure. Helium is no longer inert. It is a partner that can sulk and separate. Water is no longer a solvent. It is a crystal with liquid veins. These altered identities filter upward into the stories told about storms, belts and fields, because the interior feeds the exterior. The tools that press and shock and compute do not imitate a planet. They provide a dictionary with which to read it. He leaves the laboratories with gratitude for scale made small. A chamber between diamonds becomes a time machine that visits the first minutes after assembly when heat was thick. A shop platform becomes a tunnel into depths that sunlight never touches. A cluster of processors becomes a thought experiment that would be impossible with hands. Together they let a world reveal its phases in numbers and plots, turning poetry into physics without stealing the wonder. In their company, secrets feel less like walls and more like doors shaped by pressure and temperature, ready to open when asked in the right dialect. He reads a planet by the light it writes on its own sky. Near the poles a circlet glows, a crown of ultraviolet and infrared that brightens and dims, with a rhythm set by rotation and by the flow of space around it. The glow is not the quiet echo of sunlight. It is power drawn from deep motion and paid out along magnetic highways. Electrons race downward and collide with hydrogen, splitting lines into colors that telescopes can weigh. Protons follow their own paths and heat the upper air until molecular ions sing in infrared. The aurora is a ledger. Each arc and knot records where currents enter, close, and return. A magnetosphere surrounds this world like a storm-warped balloon. Because the planet spins so quickly, the balloon is not a sphere but a disk stretched in the equator, a magnetodisk that widens until it meets the pressure of the solar wind. Inside that disk, plasma tries to keep up with rotation and often fails. The failure breeds currents. On field lines that connect middle distances to the poles, a corrotation enforcement system becomes necessary. Electric fields arise along those lines, accelerating particles so that they can carry momentum and complete the circuit. Where those fields sharpen into double layers, electrons gain the energy to paint the main auroral oval with persistent fire. Another source fills the magnetosphere with raw material. A volcanic moon bleeds gases that become ionized and trapped, forming a ring dense enough to be called a torus. The torus shares mass with the disk as plasma diffuses outward, carrying angular momentum issues with it like a debt that must be settled. The settlement occurs through field-aligned currents that descend into the atmosphere at high latitude. Where a moon's own orbit threads these fields, bright footprints appear in the aurora, small knots that march around the polar cap with the satellite's period. Those knots often trail luminous tails, signatures of Alfvén waves launched by the moon as it plows through the magnetic flow. The music of the system climbs into radio. Close to the auroral accelerators, tenuous plasmas host a cyclotron maser instability that turns electron motion into coherent emission. The output is beamed in hollow cones that sweep through space. To a distant ear, the passage of a cone becomes an arc traced in a time-frequency plot, drifting as geometry changes. Some arcs are triggered by the volcanic moon when the beaming crosses line of sight at favoured longitudes. Others answer only to the planet's own rotation. Hectometric and decametric bands carry this song, punctuated by bursts that last seconds, fused into storms that last hours. At still longer wavelengths, kilometric radiation whispers from farther out along field lines that skirt the night side. Closer in, relativistic electrons spiral around lines of force and radiate in microwaves with a steady, cruel brightness. The belts that hold them are among the fiercest anywhere near a star. Their synchrotron emission outlines where the magnetic field is strongest and where mirror points gather particles into tight shells. The belts are neither uniform nor quiet. Waves born from temperature and isotropy foster pitch angle scattering that spills electrons into atmosphere, where they add to auroral rain. Whistler mode, hiss, chorus, and upper hybrid bands mark the ongoing conversation between particles and waves. Each mode is a page in the magnetosphere's diary, and the diary writes itself anew each day. He traces the current system with an engineer's patience. Solar wind presses on the day side and forces the outer field to reconnect, sending flux down the tail. In the long magnetotail, reconnection again closes the loop, launching plasmoids that carry mass away while flinging particles earthward along field lines. Rotation competes with this external forcing, turning field lines into a disk that prefers to corrotate. The compromise is a set of currents that sweep through the equatorial plane, close through the ionosphere, and return along auroral field lines. Where conductance in the upper atmosphere is high, those currents choose broad lanes and the auroral oval spreads. Where conductance is low, paths narrow and the glow sharpens. Thermospheric winds, heated by the aurora itself, can begin to superrotate, feeding back on the pattern by altering conductance and drag. He listens for the deep origin of the magnetosphere's asymmetry. The dynamo below is not perfectly centered, and the field that emerges arrives with quirks. Some longitudes harbor patches of stronger flux. Others reveal dents in the alignment of the dipole. When these quirks map along lines to the poles, the aurora shows preferred sectors where arcs bite deeper or split. Radio arcs respect the same geometry, appearing more often when the beaming cones intersect observers at longitudes linked to the stronger sector. The magnetosphere thus carries a fingerprint from the metallic sea, and the ionosphere photographs it as luminous cartography. Waves act as couriers for stress. When a moon perturbs the flow, an Alfvénic wing forms, a pair of standing waves that carry momentum along field lines to the ionosphere. There the waves deposit energy without the need for large static voltages, producing a class of aurora that flickers at the wave frequency and marches with the satellite. When the middle magnetosphere lags behind corrotation, field lines stretch and a different regime appears, one where quasi-static potential drops accelerate particles and produce more stable arcs. The coexistence of Alfvénic and quasi-static acceleration gives the polar cap both a flutter and a spine, a dynamic edge and a steady rim. The energy budget declares priorities. In this system, the largest contribution to auroral power often arises from rotation rather than from the solar wind. The planet's spin drags the plasma and the field, and the magnetosphere insists on keeping up. The price is paid in Joule heating and particle precipitation that together outshine many stellar drivers. Yet the sun is not absent. During high-pressure gusts, the dayside compresses, the nightside tail stores flux and then releases it, and the ovals brighten in response. The blend of internal and external driving lifts the aurora beyond a single cause and turns it into a weather system of space. Instruments ride through this architecture and convert motion into numbers. Particle detectors count distributions that change with latitude and local time. Field sensors read vectors that twist on scales from seconds to hours. Radio receivers register the cut and curl of arcs and bursts. Ultraviolet imagers map the main oval, the polar emissions beyond it, and the footprints of moons. Infrared spectrometers weigh the heat carried by molecular ions and trace winds that spin faster than the planet itself. The data align to show that the auroral oval is not a single ring. It comprises a main emission linked to corrotation breakdown, a polar cap influenced by solar wind coupling, and discrete spots from satellites that shine like pearls on a turning thread. He follows a line from pole to interior and watches its character change. In the upper atmosphere, collisions dominate and currents close through conducting layers shaped by chemistry and sunlight. Farther out, adiabatic invariants guide particle motion, and mirror points rise and fall with field strength. Deeper still, in the conducting sea, the same field lines are frozen into flows that wind and tilt them. The coupling is intimate. A change in heat delivery to the dynamo can alter the field, which shifts the mapping to space, which reorders where aurora and radio speak loudest. The chain is long, yet the links hold. A single field line is a thread that stitches the metallic ocean to the sky. He saves room for subtleties that complicate the map. Dawn and dusk sectors differ because gradient and curvature drifts separate ions from electrons. The night-side tail hosts injections that arrive in bursts and paint transient spots inside the main oval. The dayside cusp admits fresh plasma along newly opened field lines, creating patches where the aurora murmurs with a different spectrum. Even the footprints of moons are not single sparks. They often show a lead and a trail, a primary and a secondary spot, and a faint ribbon that winds away as the alphenic disturbance echoes around the planet. Radiation shows its teeth to visiting machines. High-energy electrons in the inner belts destroy detectors that linger. To reach close orbits, a craft must thread paths that minimize time inside the fiercest zones, diving over the poles where protection is greatest. Even there, bursts and belts sting. The very cruelty that makes this magnetosphere famous becomes a measuring stick. The depth and hardness of the belts betray the topology of the field, the history of injections, and the balance of wave-particle processes that shape pitch angles and lifetimes. He imagines silence for a moment, and then repopulates it with known voices. The ultraviolet oval hisses at wavelengths shaped by atomic hydrogen. The infrared ring hums through molecular ions, heated to thousands of Kelvin. Radio arcs sweep past, tied to cones that scissor the sky as the planet spins. Microwave belts shine with a steady bruise from electrons that refuse to leave. Each voice carries timing that reflects rotation, modulation that reflects beaming geometry, and drift that reflects the slow breathing of the magnetodisk. Together, they form a survey of invisible currents, rising from depth and returning through poles. The poles are not merely endpoints. They are engines in their own right, where momentum exchange with the upper atmosphere feeds back on the whole. Winds driven by Joule heating can drag the ionosphere ahead of the deep interior by a measurable fraction. That drag, in turn, alters the path of closing currents and the structure of the main oval. The system teaches an old lesson in a new register. Magnetism, rotation, chemistry, and radiation do not live in separate chapters. They are verbs in the same sentence, spoken along field lines that tie a liquid metal sea to a bandwidth of light. He ends with the idea that listening is mapping. To record an arc in radio is to draw a cone in 3 dimensions around a pole. To watch a footprint shimmer is to sketch a current that leaves a moon, climbs a field, and lands in air. To measure microwave bruises is to contour the hardest parts of the belts against the strongest bends in the field. None of these require a photograph. All of them reveal structure as surely as a camera would. The magnetosphere is both shield and storyteller, and its stories rise from depths no probe will touch, then bloom as aurora that any eye can find if given the right glass and a patient night. He looks upon a world that wears clouds like a covenant. The bands move, the spots breathe, the poles glow, yet none of it discloses the final page. Opaque decks protect a machinery that chooses pressure as its grammar and temperature as its pulse. The protection is not hostility, it is a reminder that depth is a right reserved by gravity. What lies beneath is not a picture, it is a process. The process is not a trick, it is a patience. A visitor who wants assurances will leave with better questions, and that is the tribute the planet collects from curiosity. What the clouds protect is a ledger of heat that predates seasons. The number of watts rising from within is not a decoration. It is inheritance, contraction held in a slow fist, chemical separation converted to glow, and a balance that changes only as centuries stack like pages. Clouds take that ledger and spend it in patterns that convert warmth to motion, and motion to structure, and structure to memory. The memory is written in jets that insist on their lanes, and in vortices that insist on their circles. The ledger remains hard to read directly, because the clouds have chosen to speak in the voice of weather, while the sun beneath is geology of gas. What the clouds protect is a parliament of phases that do not occur above sea level on a smaller world. Hydrogen that can sparkle as a metal without becoming a crystal. Water that can hold a lattice of oxygen while letting hydrogen run like a city of lightning. Helium that can forget companionship and fall as a quiet rain. These states are not rare curiosities tucked in corners. They are the bulk of a world that measures in tens of thousands of kilometers, a globe where identity changes with depth, and depth is the most common direction. The clouds are the modest face of a complexity that prefers not to brag. What the clouds protect is a map of compositional slopes that carry biography. Heavy elements are not scattered randomly throughout. They gather where pressure invites, thin where buoyancy resists, and settle into gradients that remember the youth of the system. A seed might have formed in pebbles, or a fragment might have swallowed gas first, yet the proof is now a watercolour rather than an engraving. The clouds float above that watercolour, and every tint they show is influenced by that hidden distribution. To change the map beneath is to change the palette above, but the causal chain loops through mathematics that rarely yields everything it knows. What the clouds protect is a conversation between electricity and flow that speaks in fields rather than in textures. A conductor in motion builds a magnetic reach that dominates a space larger than the planet itself. The reach ripples with waves, glows with aurora, and carves belts of radiation with edges formed by line geometry, not by rock. This is not a surface phenomenon. It is a dialogue between currents in conducting shells and plasma in orbiting space, with the clouds as witnesses rather than the court. The witnesses are generous with hints, yet the transcripts are incomplete, and the unsaid becomes as eloquent as the spoken. What the clouds protect is the patience of layered exchange. Heat rises where it can move quickly, then pauses where composition requires it to slow, then leaps again when the structure allows. Interfaces form, erode, and reform. Vertical paths kink and resume. In one age the throttles tighten and the world cools shyly. In another they relax and the lantern brightens. The clouds watch all this and alter their rhythms in sympathy. They never open a single window that shows the ladder entire. The restraint is not refusal. It is a demand that the observer accept inference as a craft. What the clouds protect is the scale of variance. A human accepts variability in a day or a season. A planet of this size writes variability on decades, centuries, and what the mind calls deep time. A belt can pale and return as part of a cycle that stores energy invisibly, then spends it visibly. A crimson oval can shrink or darken as part of a longer negotiation between shear, radiation, and chemistry. The interior responds with its own tempos, a slow shifting of boundaries, a slow rearrangement of gradients. The protection offered by clouds is the protection of tempo. The face keeps rhythm while the heart writes melody too slow to hum. What the clouds protect is the dignity of uncertainty, not the kind born of ignorance, the kind born of richness. Data arrive as gravity signatures that whisper, as radio bursts that shout, as spectra that sing in heat. None of them lies. yet none of them translates the whole dialect. The interpreter must reconcile messages that were never meant to be one sentence. The reward is a model that is honest about its limits, a portrait drawn in careful strokes that do not pretend to show what the light cannot touch. This discipline is not a cage around imagination. It is the compass that lets imagination walk without wandering off the chart. What the clouds protect is the education of instruments. Each tool sent to listen becomes a better listener for the next. The path that leads from optics to microwaves to gravity to magnetism is a curriculum, not a tour. The clouds insist that progress be cumulative rather than theatrical. They accept passage for machines that arrive with humility and readiness to hear soft tugs and quiet fields. They ignore the impatient, then reward the patient with coherence where the maps overlap. In this way, the clouds select for a certain virtue in the craft that studies them. What the clouds protect is the capacity for surprise. The next image can show a belt that changed character in a month. The next pass can tilt the scale on a harmonic that had seemed steady. The next spectrum can reveal a latitude that runs dry where wet was expected, or wet where dry ruled. Surprise is not evidence against understanding. It is evidence that understanding belongs to a living system. The clouds curate surprises the way a careful museum curates paintings, revealing them in a sequence that teaches taste and refuses a final trophy. What the clouds protect is the sanity of natural law. Every strange phenomenon that appears in this world obeys equations that would hold in any laboratory given enough pressure and enough patience. The unfamiliar is not lawless. It is simply operating in a part of phase space where the daily life of a small world never ventures. Pressure closes gaps in knowledge. Conductivity opens pathways for force. Rotation assigns structure to motion. Each principle keeps its oath. The clouds hide nothing that violates the oath. They hide the straightforward application of the oath to scales that overwhelm intuition. What the clouds protect is the relevance of wonder. Knowledge widens the view rather than narrowing it. A picture that adds a metallic ocean and helium rain and ladders of heat does not reduce beauty to mechanism. It multiplies awe by adding believable depth. The more one learns about how pressure writes, the more the surface bands become sentences. The more one learns about how chemistry trades partners at temperature, the more a colour becomes a diary entry. Wonder that relies on ignorance is fragile. Wonder that relies on comprehension is resilient. The clouds protect the resilient kind by asking that every image be a preface. What the clouds protect is a mirror. A small world of rock learns to see its own biases reflected in a giant that rejects them. Expectation arrives with images of surfaces and edges, of shorelines and horizons. It leaves with respect for gradations and for systems that have no flaw. Expectation arrives wanting answers that will close the book. It leaves with questions that open better ones. The mirror is not insult. It is instruction. A world of weather without ground instructs a world of ground about what counts as foundation. What the clouds protect is the future tense of inquiry. There will be another instrument that listens to a frequency not yet used. There will be a calculation that runs long enough to remove a doubt. There will be a laboratory trick that holds pressure just a little longer and decides an argument between two phase maps. There will be a quiet orbit with a geometry that crosses a region scarcely sampled. The clouds do not forbid these events. They shelter the terrain until the craft is ready. Protection then yields to revelation, and revelation yields to better protection as comprehension grows. He watches the bands again and feels no urgency to force a final line. The gas giant keeps its clock under clouds, and the clock is precise, generous, and unwilling to be rushed. The value lies in the cadence, in the way lessons appear at the rate they can be absorbed. What lies beneath is not a treasure box to be emptied. It is a school that never graduates anyone early. The clouds are the threshold that keeps the lessons ordered. The threshold is firm, yet it opens to those who learn the language of tugs, fields, and faint brightness. That language is quiet, and the quiet is the secret the clouds protect most of all. Night gathers on the limb, and the planet does not dim so much as deepen. Bands drain into a dark that is not absence, it is volume. Far above, the ring of aurora keeps its watch, patient as breath, fast as thought. Somewhere inside, hydrogen remembers the trick it learned, under pressure, and continues to carry currents through a sea without shore. Somewhere higher, helium decides again to fall, writes another fraction of a degree into the long arithmetic of cooling, lets another corridor of heat change its mind. Somewhere lower, a gradient reforms its edge, a step in a staircase that no eye will draw, a hinge in the story of transport. He listens for silence, and finds only low voices. Gravity keeps speaking in careful numbers. Microwave light returns with hints of dryness and wetness that sketch unseen rivers. Radio arcs rise and fade, turn geometry into time. None of it competes with the clouds, all of it trusts them. They are the custodians of scale, the curators of patience, the right kind of veil. It is easy to love what can be seen, and easier still to love what can be touched. Here the love must be for inference, for the ways the unseen agrees across instruments that never met. That agreement is a kind of tenderness. The lantern of the planet glows in infrared with energy earned at birth and edited by age. It warms storms that climb, it warms belts that sink, it warms a memory that weather translates into colour and motion for those who care to watch. A world like this asks for nothing except attention without hurry. To offer that is to see that secrets are not refusals. They are invitations with long dates. The clouds hold the invitation out, and the night around the bands feels wider than space.